Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us to the very beginning of motion itself, to the moment we realised the universe was not still, and that everything we see, from galaxies to grains of dust, is part of a great silent drift outward. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the story of how the universe began to move. And if your mind starts to wander, that's perfectly fine. The universe has been wandering too for nearly 14 billion years. For most of human history, the cosmos was thought to be still, perfect, eternal. The stars hung above like jeweled pins fastened to a dark celestial dome. To ancient astronomers, this immobility was not a question. It was comfort. The heavens, they thought, reflected divine order. The Earth sat quietly at the centre, unmoving, while everything else revolved around it in smooth, eternal circles. In Greece, philosophers like Aristotle believed that the heavens were made of a pure substance called ether, untouched by decay or change. It was a universe of certainty, one that could lull even restless minds into believing that nothing truly shifted, that all motion was cyclical, predictable and safe. Centuries later, that stillness began to tremble. Galileo turned his telescope to the sky and saw moons orbiting Jupiter, proof that not everything circled the Earth. Newton then gave the heavens a new kind of order, not one built on perfection, but on law. He showed that the same invisible hand pulling an apple to the ground guided the planets in their paths. Gravity, he said, was universal. Space was an empty stage, fixed, absolute, unchanging, where the drama of motion unfolded. For the first time, motion itself became natural, yet even Newton's universe, full of moving stars and falling worlds, remained fundamentally static as a whole. Its architecture was eternal, its balance perfect. Everything might move, but nothing truly changed. When Albert Einstein entered the scene, he imagined something even grander. He no longer saw space as a rigid framework, but as something flexible, something that could bend and ripple with energy. His equations of general relativity described the universe as a single fabric woven from both space and time. Gravity was no longer a pull between distant objects. It was the soft curvature of that fabric around mass and energy. But there was a problem. When Einstein applied his equations to the entire cosmos, they refused to stay still. The mathematics suggested that space should either expand or contract. It could not remain static. The universe, by its very nature, wanted to move. Einstein didn't like that idea. He preferred a calm, eternal universe, much like everyone else at the time. So he added a small correction, a term he called the cosmological constant. You can think of it as a quiet counterbalance, a subtle pressure that kept gravity from pulling everything together. It was his mathematical way of saying, "Please, stay still." Later, he would call it his greatest mistake, though. As we'll see, it might have been one of his most prophetic insights. For the moment, though, the world remained convinced that the cosmos did not move. If the night sky looked unchanging, why should the universe itself be expanding? Stars rise and set, constellations shift, but the great pattern endures. To imagine the whole of existence growing or shrinking was absurd, like thinking the stage itself might breathe along with the actors. And yet, a few quiet voices began to suspect that something wasn't as steady as it seemed. By the early 20th century, telescopes had grown powerful enough to peer deep into the faint haze of distant galaxies. What astronomers saw there would slowly unravel the ancient stillness. One of them, a soft-spoken observer named Vesto Melvin Slifer, began to study the light from faraway spiral nebulae, what we now know as galaxies. He noticed something odd. The colours in their light were shifted slightly toward the red end of the spectrum. It was as if the light waves had been stretched, like the low hum of a car engine receding down a long road. This redshift, as it came to be called, hinted that those galaxies were moving away. Still, few believed this meant the entire universe was expanding. Maybe just a few galaxies were drifting. Maybe the motion was local. Even Einstein, when told about these observations, brushed them aside. But somewhere in Belgium, a young priest physicist named Georges Lemaître was quietly following the math where it led. If space itself was allowed to move freely, he realised, then the simplest and most natural behaviour of the universe would be expansion. Not an explosion, but a gentle swelling. Space stretching rather than objects flying through it. He imagined everything that exists once gathered in a single, dense point of energy and light, a primeval atom, as he called it, that unfolded into all we see today. At first, his idea was dismissed. "Your calculations are correct," Einstein said when they met, "but your physics is abominable." Yet a few years later, an American astronomer would make observations so striking that the entire world would have to reconsider. That astronomer was Edwin Hubble. On clear nights at Mount Wilson Observatory in California, Hubble studied galaxies through a telescope so massive it looked like a cannon pointed at infinity. What he found changed everything. By measuring the distances to those galaxies and comparing them to their redshifts, he discovered a simple, beautiful relationship. The farther away a galaxy is, the faster it seems to recede. Space itself must be stretching, carrying galaxies apart like raisins carried outward in rising dough. This law, the quiet rhythm of expansion, became known as Hubble's law, though Lemaitre had predicted it first. The discovery was not a bang but a whisper. It didn't roar across the world in a single night. It crept gently into human understanding, like dawn revealing what had always been there. The universe was not a still painting. It was a living fabric, swelling with time, and somewhere within it, on a small planet orbiting a modest star, one curious species finally noticed. The universe, it turned out, had never been still. It only looked that way because we had been standing inside the motion all along, like passengers on a ship so vast we could not feel its drift. And now, the quiet realization had arrived. If everything is moving apart, then at some time in the distant past everything must have been together. All of space, all of matter, all of light, folded into one breathless beginning. Our quiet exploration now turns to that breath itself, to what it means for space, not objects, to expand. The story of how we came to know that the universe is expanding begins not with theory, but with light. Starlight is our oldest messenger. It travels across unimaginable distances, carrying secrets in its faint shimmer, secrets about motion, distance, and time itself. Every beam of light, even the quietest one, is a letter written in the oldest language of the cosmos. All we need is patience and the right kind of eyes to read it. When Vesto Melvin Slifer looked at the skies in the early 1900s, he didn't have the enormous telescopes or the computer-guided instruments we use today. What he had was a spectrograph, a device that spreads light into its colours like a prism. When you pass sunlight through such a device, you see not just a rainbow, but also dark lines, tiny gaps where certain colours are missing. These missing pieces correspond to the fingerprints of elements like hydrogen, helium, and calcium. Every atom leaves its mark on light, like a signature written in colour. Slifer examined the light from spiral nebulae, those fuzzy smudges of light scattered across the night sky which no one yet knew were galaxies far beyond our own. He expected their spectra to look similar to stars, And they did, except the pattern of lines was shifted, not by much, but enough to notice. The lines had all moved toward the red end of the spectrum as if the light had been stretched on its long journey. This was the first sign of something remarkable. The universe itself might be in motion. To understand, I think of sound. When an ambulance passes you on the street, its siren seems to change pitch. It's higher as it approaches and lower as it moves away. That's called the Doppler effect. The same thing happens with light, but instead of pitch, it's colour that changes. If a star moves away, its light stretches, shifting toward red. If it moves closer, it compresses, shifting toward blue. What Slipher had seen was the cosmic equivalent of 1,000 ambulances, all heading away from us at once. He shared his findings quietly without grand claims. Many scientists assumed those nebulae were simply part of the Milky Way, perhaps clouds of gas drifting within our own galaxy. The idea that they might be separate island universes, each full of stars like our sun, was controversial. The scale was too vast, too humbling. But across the ocean, another astronomer was already beginning to measure just how far away those islands might be. Edwin Hubble worked at Mount Wilson Observatory in California, a place where the night air is thin and still, the stars sharp enough to seem almost touchable. Through the 100-inch Hooker telescope, the largest of its kind then, he began a long, patient survey. His goal was to determine the distances to the faint smudges of light in the sky. He used variable stars, special kind of stars whose brightness changes rhythmically, almost like a heartbeat. By comparing how bright these stars appeared from Earth to how bright they truly are, Hubble could estimate their distance. The results were astonishing. The nebulae weren't part of the Milky Way at all. They were entire galaxies, millions of light years away. And when Hubble compared their distances to their redshifts, the stretching of their light, he saw a simple, elegant pattern emerge. The farther away a galaxy was, the faster it seemed to be moving away. If a galaxy twice as distant receded twice as fast, and one 3 times as distant moved 3 times as fast, there had to be a rule behind it. The universe wasn't random, it was following a rhythm. That rhythm became known as Hubble's law. We can describe it softly like this. For every million light-years of distance, a galaxy moves away at roughly 70 kilometers per second. In words rather than numbers, that means if you could look at a galaxy 1 million light-years away, it would be receding faster than a speeding bullet, 10 million light-years away 10 times faster, 1 billion light-years away faster still. This wasn't just motion within space, it was motion of space. The distances themselves were growing. The very fabric of reality was stretching. To visualize it, imagine a loaf of bread rising in the oven, its dough dotted with raisins. Each raisin represents a galaxy. As the bread expands, the raisins move apart. But none of them are actually traveling through the dough. They're carried apart because the dough itself is growing. Every raisin sees every other raisin receding, no matter where it sits. There is no single center of expansion. Every point feels like the middle. That is our universe, a rising loaf of space, expanding evenly in all directions, not from one location, but from everywhere at once. Hubble's discovery confirmed what Lemaitre's equations had quietly predicted. The universe is not static. It has a history, a rhythm, and, most startlingly, a beginning. If the galaxies are moving apart today than long ago, they must have been closer together. Follow that backward far enough, and you reach a moment when all of space, time, and matter were compressed into a single, brilliant point. The primeval atom that Lemaitre described. What we now call the Big Bang. It's important to remember that this bang wasn't like an explosion in space. It was an expansion of space itself. There was no air, no fireball, no edge pushing into a surrounding void. It was more like a deep inhale that began everywhere at once. If the universe could be said to have a center, that center is everywhere. Every atom, every patch of sky, Every place you can point to was once part of that same beginning. Still, Hubble's discovery raised as many questions as it answered. Why is the universe expanding? What drives that motion? Will it keep expanding forever, or will gravity eventually pull it back together? At the time, no one knew. But even without answers, the implications were staggering. The universe wasn't eternal. It had a past. And if it had a past, it might also have a future. The simplicity of Hubble's law hides a quiet depth. It tells us that the universe has a kind of built-in tempo, a measure of how quickly the cosmic fabric stretches. Astronomers call this rate the Hubble constant, though it's not truly constant across all time. It changes as the universe evolves. But we can describe it in gentle words. It is the heartbeat of the cosmos, the pace at which distance itself grows. When you think about that, it becomes strangely intimate. Every second, every moment, the space between galaxies grows a little wider. But the space between you and the person sitting beside you does not. Gravity, chemistry, and the quiet strength of atoms keep small things together, while the vast void between galaxies drifts apart. The expansion of the universe is both everywhere and almost nowhere at once. It lives only in the stretches too wide for our senses to feel. For Hubble, the discovery was not dramatic. It was mathematical, observational, methodical. Yet its meaning reshaped everything. A universe that expands must have begun. A universe that began must have come from something, or perhaps from nothing at all. And in that nothing, everything we know was waiting to unfold. As we follow this trail of light, we begin to see that space is not an empty background, but an active participant in the story. It stretches, it carries, it breathes. The universe, as Hubble revealed, is not a stage upon which events play. It is the play itself still being written, and with every passing second its sentences grow longer, its fabric wider, its rhythm softer but unending. The cosmos is expanding, not into something, but into itself. And so our path now carries us deeper into that strange idea. What does it truly mean for space to expand? What is this fabric made of, and how can emptiness itself have motion? When we look out into the night sky, we're not just looking into distance, we are looking back in time. Each point of light is a message that has crossed the years to reach us. The farther the light, the older the message. A galaxy 1 billion light years away shows us what it looked like 1 billion years ago. Beyond that lies a faint glow, a whisper of light so old it comes from the moment when the first atoms were born. The deeper we look, the younger the universe becomes, until we approach a moment when there was no light at all, only energy, compressed and waiting. This realization that the universe had a beginning was first written not in poetry, but in mathematics. In the early 1920s, Georges Lemaitre, a Belgian priest with a passion for physics, took Einstein's equations of general relativity and asked a simple, daring question. What if we allow them to describe a universe that changes with time? Einstein's equations relate matter, energy, and the geometry of space itself. They can be thought of as saying, the shape of space tells matter how to move, and matter tells space how to curve. When Lemaitre solved these equations for the cosmos as a whole, he found that space could not sit still. Its natural behaviour was to expand or to contract. To make this image gentle for the imagination, think of the universe as a soft, stretchable fabric. Galaxies are not flying through it. They are sewn into it, like beads woven into cloth. If the fabric stretches, the beads move apart, not because they are pushing themselves away, but because the space between them grows. This idea is the heart of the model that physicists still use today, the one often called the cosmic scale factor. It's a way of describing how large the universe is compared to its earlier self. You can think of it as a kind of cosmic metronome. When the universe doubles in scale, the distances between galaxies double too. But Lemaitre's insight didn't stop there. If space is expanding now, it must have been smaller in the past. And if we continue to reverse time in our minds, like rewinding a film reel, the galaxies draw closer and closer, the distances shrink, the light grows hotter and bluer, and eventually everything converges into a single point of immense density. Lemaitre called this the primeval atom. To him, it was not an explosion in space, but the birth of space itself. The entire cosmos once existed as an incredibly dense seed, smaller than a grain of sand, packed with every particle, every law of physics, every possibility. When that seed began to unfold, time itself began with it. He imagined this beginning not as chaos, but as order emerging from simplicity. The laws of physics, gravity, electromagnetism, the forces that hold atomic nuclei together, were not separate yet. They were one. In the early moments, there were no stars, no galaxies, not even atoms. The universe was pure light and energy, an ocean of brightness too intense for form to survive. Only when it cooled slightly did matter as we know it begin to appear. At first, few took Lemaitre seriously. The idea that the universe had a definite beginning seemed too theological, too mystical. Many scientists preferred the notion of a steady, eternal cosmos, where new matter simply appeared as the universe expanded, a way to keep things timeless and comfortable. Einstein himself rejected the primeval atom, saying the concept was too religious. But Lemaitre saw no conflict between faith and physics. To him, the origin of the universe was not a miracle in defiance of nature. It was nature's most beautiful law. As the decades passed, evidence began to accumulate that supported his vision. In 1948, scientists predicted that if the universe began in a hot, dense state, there should still be a faint afterglow, leftover radiation, cooled by expansion, filling all of space. And in 1965, two engineers, Arne Penzias and Robert Wilson, accidentally found it while testing an antenna in New Jersey. No matter where they pointed, they detected a soft hiss, a background hum of microwaves. That hum turned out to be the ancient light Lemaitre had predicted, the afterglow of creation itself, now chilled to just a few degrees above absolute zero. It was the cosmic echo of the primeval atom, still resonating after almost 14 billion years. So what exactly was that moment like? The language of physics can describe it only approximately. If we try to trace back all the way to the first instant, we encounter what scientists call a singularity, a point where our current laws break down. But that word, singularity, can be softened into something more understandable. It's simply the boundary of our knowledge, the point where mathematics becomes silence. It doesn't necessarily mean an infinite point of nothingness, but rather a state where our familiar ideas, distance, time, temperature, lose meaning. We can imagine the earliest universe as smaller than an atom, hotter than 1 trillion suns, and denser than anything our minds can hold. But the exact details remain hidden behind the veil of that first light. In the language of equations, the universe's behaviour is governed by what scientists call the Friedmann equations. But we can whisper them into words instead of symbols. They tell us that the rate of expansion depends on how much matter and energy the universe contains. Too much matter, and gravity slows everything down, perhaps even reversing the expansion someday. Too little, and space keeps stretching forever. For now, the expansion continues gently, like a long exhale. Every second that passes, the fabric of space grows, carrying galaxies apart like leaves floating on a widening pond. Yet from our small perspective, everything feels still. We don't sense this cosmic stretching because it acts only over enormous distances. Within our solar system, gravity holds firm. Within our bodies, electromagnetic bonds hold atoms tight. The universe breathes, but we breathe within it, moving with its pulse. It is humbling to think that every atom in our bodies, the carbon in our cells, the calcium in our bones, the iron in our blood, was forged in stars that were themselves born from the cooling of that first fireball. We're made of the universe's memory. When we look up at the stars, we're seeing not strangers but family, tiny fragments of the same ancient seed that burst open to become everything. Lemaitr's primeval atom was not just a scientific hypothesis, it was an invitation to wonder. If everything once fit into a single speck, then everything is still connected no matter how far apart it drifts. Expansion is not separation, it is continuity. The galaxies move apart, but they remain part of one unfolding whole. Even now, as space grows, the energy it carries whispers the story of its birth. Some scientists today prefer to say that the Big Bang was not a bang at all, but a quiet beginning, the universe waking up. It began not with sound, but with light, and in that light, every possibility was contained. As we drift further into the story, the next mystery unfolds naturally. If the universe is expanding, what exactly is expanding? What does it mean for space itself to grow? And how can emptiness have movement at all? Imagine standing in a field at dawn. The air is cool, the horizon soft and endless. If you close your eyes and breathe slowly, it feels as if the world itself expands with your lungs, not moving outward into something, but simply stretching from within. That's the feeling physicists try to describe when they talk about the universe expanding. It's not that the galaxies are rushing through space like runners on a track. It's that the track itself, the invisible fabric beneath everything, is lengthening. The distances between things grow, not because they are moving, but because the very meaning of distance changes. For a long time, scientists struggled to find a way to picture this strange idea. They turned to simple analogies, ones that anyone could imagine. The first was the balloon. If you draw small dots on the surface of a balloon and begin to blow it up, the dots move away from each other. None of them is special. No dot sits at the centre. The balloon surface itself expands, and with it the space between the dots. The important part of this image is not the air inside the balloon. That's just for visualization. The true universe doesn't have an inside or an outside. It's more like the surface of the balloon itself, two-dimensional in the analogy, but three-dimensional in reality, stretching everywhere at once. Another example, just as comforting, is the raisin bread. When bread dough rises, the raisins drift apart. The dough represents space, the raisins are galaxies. As the dough expands, every raisin sees every other raisin moving away. None of them needs to travel through the dough, they are simply carried along by its swelling. It's a beautiful metaphor because it feels homely and familiar. You can almost smell the yeast, feel the warmth of the oven. But like the balloon, it has a flaw. The bread expands into the oven's air, and the balloon expands into the room. The universe, however, has no surrounding space to expand into. It is the space. To understand this better, we can soften the mathematics into a story. Physicists describe the expansion of the universe using something called a scale factor. It's not a number you can hold in your hand. It's more like a rhythm, a way of measuring how the distance between galaxies changes with time. When the scale factor doubles, distances double. When it triples, distances triple. You can think of it as the universe's own breath. Each moment of expansion is another inhalation in a cosmic cycle that so far has never paused. Now you might wonder, if space itself is stretching, shouldn't we too be stretching? Shouldn't atoms grow larger, or planets drift apart? The answer is no, and this is where the story becomes both technical and tender. The expansion of the universe acts only on the grandest scales. It affects galaxies separated by millions of light years, but it cannot pry apart objects held together by stronger forces. Gravity, for instance, binds the Milky Way tightly enough that it ignores the cosmic drift. The electromagnetic forces that hold your atoms together are far stronger still. You do not expand because at your scale, the universe's breath is too faint to feel. In a sense, this expansion is like the slow pull of a tide that only affects oceans, not ponds or puddles. It's too vast to notice, but too steady to stop. Even within the spaces between galaxies, the rate of expansion is incredibly small. Only a fraction of a percent change in distance every 100 million years. Yet given enough time, it transforms everything. When Einstein first developed his theory of general relativity, he imagined space and time as a single fabric that could bend and twist under the influence of energy and matter. To visualize this without symbols, imagine laying a sheet of rubber on a table and placing a heavy ball in the middle. The sheet dips, curving around the ball. That curvature is gravity. If you roll a marble nearby, it circles the ball because the fabric guides its path. This image helps us understand that gravity is not a force pulling things across empty space. It is the geometry of space itself. Now, extend this idea to the universe as a whole. Instead of one ball and one dip, the entire sheet is stretching outward, smoothly and evenly. The marbles, the galaxies, don't roll off the sheet. They move apart because the sheet itself is growing larger. The mathematics that describe this, often called the Friedmann-Lemaitre model, tell us how quickly that stretching happens. But rather than thinking of the equations, we can imagine an unfolding rhythm, a cosmic tempo that changes with time. Early on, when the universe was young and full of radiation and matter, gravity worked harder, trying to slow the expansion. Later, as the distances grew and matter spread thinner, another effect began to dominate, something that pushes outward instead of pulling inward. We now call it dark energy, but for now, all we need to know is that the universe did not simply explode once and then coast. It continues to expand, gently and persistently, as if carried by an invisible wind. This expansion has curious consequences. Light itself stretches as it travels through the expanding fabric. A photon, a tiny particle of light, begins its journey at one wavelength and ends it at another, longer one. It's as though space has drawn out the colour of the light during its voyage, turning blue into red, visible into invisible. Astronomers call this redshift, but you can think of it as the soft sigh of the cosmos, lengthening every note of light as it passes. When we look at distant galaxies and see their light tinted redder than expected, we are not witnessing motion through space. We are witnessing the stretching of space itself. This also means there's no edge to chase. No matter how far you travel, you never reach the outside of expansion. The universe doesn't have a boundary where it meets something else. It's more like the surface of a sphere that keeps growing, finite in what we can see, yet without borders. You can keep walking in any direction and never fall off. If we could somehow pause the cosmic movie at this very moment, we'd see galaxies scattered across a vast, mostly empty stage. Between them lies an ocean of space that's growing larger by the second. But because everything grows proportionally, there is no true centre. The expansion happens everywhere at once. It's as if every point in the universe were exhaling together. That image of a universe breathing may sound poetic, but it's close to the truth. The cosmos expands not into something else, but from itself. It is the act of becoming, not of moving. Every second, every inch of space quietly recreates itself, carrying the stars, the galaxies, and us along for the ride. And just as a breath begins without sound, so too did the universe begin in silence. A gentle widening of possibility. The next time you look up at the night sky, try to feel that motion. The light from those stars has been stretched by the same expansion that carries our galaxy away from its neighbours. We're drifting, always drifting, but not apart, only outward, together. In that slow unfolding, there is something deeply peaceful. The universe isn't racing away from itself. It's simply making room for everything it holds. As we follow this thread a little further, our journey will lead us into the fabric itself, to see what this stretching means, how it shapes light, and why the universe's quiet expansion never quite lets go. If you could see the universe not with your eyes, but with the senses of mathematics, you would see something far stranger than stars or galaxies. You would see a living fabric, a seamless weaving of space and time that bends and flexes in response to the energy within it. Every planet, every beam of light, every invisible particle leaves its mark. It is not an empty backdrop, it is the stage and the actor at once. Einstein called it space-time, though he could have just as easily called it the ocean in which everything floats. To bring this to life, imagine a vast, dark sheet stretched out before you. When you place a heavy ball in the centre, the sheet dips, curving gently downward. Roll a marble nearby, and it will spiral toward the ball, not because the ball pulls it in, but because the sheet guides its path. This is how gravity works. Not as an invisible rope tugging at distant bodies, but as the geometry of the universe itself, the gentle bending of the cosmic fabric around anything with mass. The Earth orbits the Sun not because the Sun drags it, but because the Sun's presence creates a curve that the Earth simply follows. Now take that same idea and expand it to the entire cosmos. The fabric doesn't just bend around stars and planets, it stretches as a whole. In the equations Einstein left us, this stretching can be described in terms of something called curvature and a cosmic scale factor, though we can think of them as shape and rhythm. The curvature tells us whether the universe bends like a sphere, saddles like a wave, or stays perfectly flat. The scale factor tells us how its size changes with time, whether it breathes in or out, speeds up or slows down. Together, they define the tempo of existence. In our everyday lives, we don't notice this cosmic fabric. When you drop a ball, it falls because of the Earth's gravity, a tiny ripple in that grand ocean. But the same rules that pull an apple to the ground govern the way entire galaxies move through space. The only difference is scale. The universe follows the same symphony everywhere, from the smallest drop of matter to the widest voids between galaxy clusters. At the heart of all this lies something subtle. Space and time are not separate things. They are two threads of the same cloth. When space stretches, time stretches with it. The faster the universe expands, the slower its clock ticks in comparison to the past. It's as if the heartbeat of the cosmos has been gradually slowing since its fiery birth. When we say the universe is 14 billion years old, that number itself is shaped by the expansion, by the changing rhythm of space-time. What we call age is not an absolute measure, but a reflection of how the universe itself keeps time. Einstein's equations that describe this can look intimidating when written on paper, full of Greek letters and exponents. But softly translated, they simply say, energy and matter tell space how to curve, and curved space tells energy and matter how to move. It's a conversation, one that never ends. You can think of it as a dance between gravity and geometry. A star bends space around it, and that curvature shapes the paths of planets and light. The energy in the light, in turn, gently influences the space it moves through. Everything talks to everything else, quietly, continuously. What makes this conversation so beautiful is its universality. Whether it's the pull that keeps the moon circling Earth, or the vast arcs of galaxies slowly wheeling through cosmic space, it's all the same rule, just expressed on different scales. The same curvature that makes your feet stick to the ground also helps sculpt the fate of the entire universe. To picture this, imagine space as a net made of fine, invisible threads. When you place a weight on the net, the threads stretch slightly, forming a dip. Now imagine that instead of being still, the net itself can expand or contract. Each thread lengthens, carrying with it the objects resting upon it. The distances between the knots on the net increase, but the knots themselves, the galaxies, don't change size. This is the essence of cosmic expansion. The pattern of the net remains the same, but its scale grows. In this view, nothing is truly at rest. Even when we think we are still, we are moving through this flexible web, carried by its slow drift. The atoms in your body are made of particles that hum with tiny motions, each following the curvature of space around them. When you sit quietly in a chair, you are, in a sense, surfing gently on the curvature of space-time, gliding along the same mathematical waves that guide the planets. The implications of this are profound. If the universe is a fabric, then every event, every heartbeat, every falling star leaves a ripple. Some of these ripples are gravitational waves, tiny undulations that travel through space-time at the speed of light. They're so faint that even the most sensitive instruments on Earth can barely detect them. Yet they tell us something essential. Space-time is not static. It moves, vibrates, and carries information. The cosmos is alive with motion even in its quietest moments. Now, think of how the expansion of this fabric affects light. A beam travelling from a distant galaxy is stretched as it moves through the growing universe. Its wavelength increases, its colour slides toward red. This is the same redshift we met earlier, but now we can understand it more deeply. It's not the light itself that changes, but the space it passes through. The light's wave crests grow farther apart because the ocean beneath them is widening. Every photon that reaches your eyes tonight has been reshaped by the universe's expansion, a silent testimony to the stretching of space-time. If the universe were not expanding, if the fabric were frozen, then light would keep its original pitch forever. But because it expands, the universe has a memory. Each photon carries the record of how much space has grown since its journey began. When astronomers measure redshift, they are listening to that memory. It's like hearing the echo of a song and knowing how large the hall must be from the delay in the sound. What we learn from this is that the cosmos has no centre, no edge, and no outside. There is no preferred place from which the expansion begins. Every observer in every galaxy would see the same pattern, all others move in a way. It's not an illusion. It's the natural result of living within a fabric that stretches evenly everywhere. You can think of it as the universe's way of saying, everywhere is the middle. And yet within this elegant simplicity lies an unanswered question. What happens to this expansion over time? Does it continue forever, thinning the cosmic fabric until galaxies fade from view? Or will gravity someday slow it down, perhaps pulling everything back together? The equations offer possibilities but not certainty. The future of this grand fabric depends on what fills it, on how much matter, energy, and mystery it contains. For now, the story remains open. The fabric stretches, light redshifts, galaxies drift, and we, small travellers on a small world, try to understand the pattern. When you next look at the night sky, remember that you are not looking up, but outward through time, across the rippling texture of reality itself. Every star, every photon, every heartbeat is part of that same expanding weave. If we follow the thread a little further, we'll discover that not all parts of this cosmic fabric behave the same. Some regions stretch freely, while others resist, held together by gravity's gentle grip. To understand what truly expands and what remains bound, we'll need to look closer at the limits of this cosmic motion, where the stillness of atoms meets the vastness of the void. When people first hear that the universe is expanding, it's natural to picture everything growing larger, planets drifting apart, atoms stretching like elastic, perhaps even our own bodies slowly inflating. But that isn't what's happening. The expansion of the universe is not an explosion scattering debris into space, and it's not a pulling apart of everything that exists. It's more subtle, more selective. It's an expansion of distance itself, and it only shows its strength across the grandest scales. To see why, let's start small and climb our way up. Imagine holding a coffee cup. It doesn't swell as the universe expands. The molecules inside it are bound by electromagnetic forces, which are unimaginably strong compared to the delicate stretch of cosmic expansion. These forces keep the atoms locked into place, like dancers holding one another tightly no matter how the music changes around them. Even the planet beneath your feet is immune to cosmic stretching. Its gravity far outweighs the universe's gentle drift. In fact, even on the scale of entire galaxies, the expansion cannot pull stars apart. The Milky Way, for instance, is bound by gravity so completely that it moves as one. You could wait billions of years and the distance from our Sun to the centre of the galaxy would remain nearly the same. Galaxies form families called clusters, immense gatherings of hundreds or thousands of galaxies, and even these clusters resist expansion. The only places where space truly grows are the dark, immense voids between these clusters, where gravity is too weak to hold anything together. That's why scientists sometimes say, space expands, but not everywhere. It's a bit like dough rising in the oven, but only in the parts without raisins. The dough between raisins stretches, but the clumps of fruit stay the same. Galaxies are the raisins, compact, gravitationally dense, unmoved by the rising dough of the cosmos. Expansion is not a universal stretching of matter, it's a quiet widening of emptiness. To understand this idea more deeply, let's take a journey of imagination. Picture a line of people holding hands across an open field. Each person represents a galaxy. Between them is the open air, that's space. Now, imagine that the air between them somehow grows, doubling the distance from hand to hand, but their arms remain the same length. They don't move through the field itself expands beneath them. If they are close together and gripping tightly, they resist. But if they are far apart, they drift effortlessly. That's the universe. Expansion doesn't pull on things directly, it changes the scale of the distances that separate them. Astronomers use a term for those who drift perfectly with this flow: co-moving observers. A co-moving observer is something that simply follows the expansion of the universe without resisting it. Galaxies floating in the cosmic void are such observers. They are carried along like boats on an ocean current, not by their own power but by the quiet motion of the water beneath. Here on Earth, however, we are not co-moving. Our planet, our star, our entire galaxy all dance to gravity's local rhythm, not to the cosmic one. We orbit the Milky Way centre at hundreds of kilometres per second. We spin and swirl in our local gravitational bubble, barely noticing the wider current. That cosmic current, the expansion, is incredibly slow on human scales. If we measured the rate today, we'd find that for every 3 million light-years of distance, galaxies recede about 70 kilometres per second farther apart. That sounds fast, but across the immense reaches of space, it's gentle, a steady hum rather than a roar. Translating it into more familiar words, the universe's growth is like adding the width of a human hair to the space between the Milky Way and its neighbours every year. The cosmos breathes, yes, but with the patience of eternity. Still, this quiet expansion shapes everything we can see. Light itself, as it travels through this stretching fabric, becomes part of the expansion's story. A photon, that tiny spark of light, doesn't stretch in the way we might stretch a string. Instead, its wavelength grows longer because the space it crosses is expanding. Every crest and trough of the wave is carried outward, its rhythm slowed. This is the reason distant galaxies appear redder than they should. The longer the light travels, the more it's pulled across an expanding ocean of space, and the more its colour slides toward red. This isn't a property of the photon itself, it's a property of the journey it takes. Some people wonder whether this means the photon is losing energy. In a way, yes, but not in the usual sense. Energy is not lost to friction or absorption, it's spread over a larger stretch of space. The universe doesn't waste the energy, it transforms it into the rhythm of expansion itself. We could say that the cosmos, by stretching light, is writing its story into every ray that reaches us. If we could shrink ourselves down to the scale of atoms and molecules, we'd see that these tiny worlds are completely oblivious to the cosmic stretching. The strong nuclear force inside an atomic nucleus, the electromagnetic bond that holds electrons in orbit, these are so powerful that even the grand breadth of the universe cannot touch them. The ratio is staggering. The energy holding together two protons is trillions upon trillions of times stronger than the faint push of expansion across the same distance. It's like comparing the strength of a mountain to the weight of a single feather resting on its summit. And so, the expansion of the universe is both everywhere and almost nowhere at once. It fills all of space, yet it is too weak to move anything we can touch. It shapes the fate of galaxies, but it leaves our morning coffee undisturbed. It is the background rhythm to everything else, too slow for our senses but too vast to ignore. You might imagine the universe as a giant patchwork quilt. Each patch represents a region of space, a galaxy, a cluster, a cosmic void. Within the stitched patches, everything holds firm, but between them the seams slowly lengthen, ever so slightly. The pattern remains, only the scale changes. That gentle, steady widening is what we mean by expansion. This understanding also explains why we cannot detect the expansion locally. Astronomers on a distant galaxy would make the same observations we do. All other galaxies receding, all space stretching evenly in every direction. No matter where you are, the view looks the same. It's as if the fabric of the universe has no privileged centre. Every observer feels as though they're in the middle of the unfolding because, in a way, they are. The expansion happens everywhere at once. And yet, even this explanation feels incomplete. We can describe what expands and where, but we still haven't answered the deeper question: why? What is causing space to stretch? Why does the universe refuse to sit still? For that, we need to turn to a mystery that even Einstein's elegant equations couldn't predict. A mysterious form of energy that seems to live in the vacuum itself, pushing galaxies apart with quiet persistence. Before we reach that mystery, let's pause to reflect. Everything we've discussed, from galaxies to atoms, from light to time itself, shares a single rhythm. The universe expands, but not all of it listens to that rhythm equally. In the spaces between, in the grand silence of the void, the expansion sings. Within the galaxies, within you, within the warmth of a cup of tea, gravity and chemistry play their own songs. The universe is a choir of different tempos, some cosmic, some human, all woven together in a harmony we're only beginning to hear. As we drift gently forward in this story, we'll begin to listen for that quiet note of acceleration, the invisible pressure that drives the universe's widening breath faster and faster. What is this hidden force that fills the emptiness? What is the energy of nothing itself? Every night, when you look up at the stars, you're really looking at colours stretched thin across time. Each beam of starlight is a record of how much the universe has grown since it left its source. Light, as gentle as it seems, is elastic, not in itself, but in the journey it takes. As space expands, the waves of light travelling through it expand too. The longer the journey, the more the waves are drawn out, their colour shifting slowly toward red. This quiet stretching is what astronomers call redshift, but it might just as well be called the universe's soft heartbeat, a pulse we can see in colour. To imagine this, think of a long, slow violin note played in a room that keeps growing. The sound's pitch falls as the room expands, because each echo must travel a little farther before returning. Light behaves in much the same way. Its waves are like the ripples of that note, stretched by the ever-widening hall of space. The longer it travels, the more its rhythm slows. By the time the light from a distant galaxy reaches our telescopes, the colour it once had has deepened. Blue becomes red, visible becomes invisible. It's a kind of cosmic aging, light, growing older with distance. But not all colour shifts in the same way. There are three main ways light can change its tune, and though they sound different, they are all parts of the same cosmic symphony. The first is the Doppler effect. familiar to anyone who has heard a siren wail as an ambulance passes by. The sound waves are squeezed together when it approaches and stretched apart as it recedes, making the pitch drop. Light waves behave the same way when an object moves through space. Approach brings a bluish tint. Retreat brings a red one. This is the simplest kind of redshift, caused by motion itself. The second kind is gravitational redshift, born not from motion, but from the weight of gravity. Light climbing out of a gravitational well, say escaping from the surface of a massive star, loses a little of its energy to the climb. The climb doesn't slow it down, because light always travels at the same speed, but it does lengthen the wave, softening its colour. You can imagine it like a runner ascending a hill, who still moves at the same pace but breathes a little harder with every step. The colour of light tells us how steep the hill of gravity was that it had to climb. The third and most mysterious is cosmological redshift, the kind we see when light travels across expanding space. Here, the stretching doesn't come from motion or gravity, but from the growth of the universe itself. Imagine drawing a wave on a rubber band, then gently pulling the band apart. The wave becomes longer, not because the marks moved, but because the space between them increased. That's what happens to every photon as it journeys through the cosmos. The light isn't running away, the road beneath it is simply stretching. Though these three forms of redshift sound distinct, in the language of relativity they are one and the same, different expressions of how light interacts with space-time. Whether the shift comes from motion, gravity, or expansion, the principle is identical. Light records the geometry of the universe in its colour. Every wavelength is a story, and every colour a time capsule. To test this, scientists have used clever experiments on Earth. In 1959, two physicists, Robert Pound and Glenn Rebka, performed a delicate measurement at Harvard University. They sent beams of gamma rays up a tower and measured the tiny shift in their energy between the base and the top. The results matched Einstein's predictions perfectly. The light had lost a trace of energy climbing the Earth's gravitational field. It was a microscopic version of the same process happening across galaxies, a tiny echo of the universe's grander stretching. This discovery revealed something extraordinary. Light, in all its speed and brilliance, is deeply sensitive to the shape of space. It is not merely a traveller through the universe, it is a witness to its changes. When astronomers look at distant galaxies, the redshift in their light tells them not only how far those galaxies are, but how much the universe has expanded since their light began its journey. The colour of the galaxy is a timestamp written in the oldest language there is. If we could convert that colour back into distance, we would find that the farther a galaxy is, the redder it appears. This is Hubble's law told in shades of light, a direct connection between colour and cosmic history. A galaxy with twice the redshift is roughly twice as far away and its light twice as old. Each photon, each colour, is like a page in the diary of space, recording the expansion in its wavelength. Now, there's something quietly beautiful about how this stretching interacts with time. The light from a distant quasar, one of the universe's brightest beacons, may have left when the cosmos was only a fraction of its current age. As it travelled through billions of years of expansion, its wavelength grew thousands of times longer. By the time it reaches us, it may no longer shine in visible light at all, but in the microwave glow of the sky. In that transformation is the universe's entire story, a flash of blue fire that, across aeons, becomes a whisper of warmth. Even the afterglow of the Big Bang, what we now call the cosmic microwave background, follows this same rule. That ancient radiation once blazed with the light of a white-hot universe. But as space expanded, its colour stretched into microwaves, its temperature cooled to just above absolute zero, and its light became invisible to our eyes. The universe itself has aged through colour, from brilliant white to faint red to the cool grey of twilight, and yet that faint glow still fills every inch of the sky, a reminder of what light remembers. What's truly fascinating is that this cosmic redshift also reshapes how we think about time. When we see light from a galaxy billions of light years away, we're seeing it not as it is, but as it was. The light carries the memory of that ancient moment, unchanged except for its stretched colour. In a very real sense, looking at distant galaxies is like looking through layers of time. The deeper we gaze, the younger the universe becomes until we reach the first flickers of starlight, the cosmic dawn. This idea that colour and time are entwined is deeply poetic. It means that every sunset you've ever seen is part of the same phenomenon that reveals the universe's expansion. The reddening of the sky at dusk, caused by sunlight scattering through a thicker layer of air, is a small echo of cosmic redshift. The same gentle logic applies on every scale. The farther light travels, the more it bends toward warmth. So when we speak of redshift, we're really speaking of the universe breathing through colour. Every photon that reaches us has been changed by the space it crossed. Every hue in the night sky is a note in the song of expansion. The galaxies do not flee through emptiness. Rather, the fabric of reality between us has been quietly stretching, turning their bright blue songs into deep crimson sighs. As we follow this thread further, we begin to wonder, what kind of shape does such a fabric take? If space stretches, can it bend as well? Is the universe curved like a sphere, or does it stretch flat and endless like a sheet? Our next step leads us toward that question, the geometry of the cosmos itself, and the strange possibilities hidden in its shape. If the universe is a fabric, then it must have a shape. Not a shape we could see from the outside, there is no outside to stand in, but a shape that determines how distances behave, how light travels, and how the story of expansion unfolds. When we say the cosmos is expanding, we're really talking about how this invisible geometry changes with time. Its shape is not drawn in lines and angles, but in the way space curves around matter and energy. To understand the universe, we have to learn to see curvature not as a bend in something visible, but as a hidden rhythm in the distances between things. In Einstein's description of space-time, matter and energy, tell the fabric how to curve. If the universe contained no matter at all, only pure emptiness, its geometry would be perfectly flat, like a sheet stretched evenly in all directions. But our universe does have matter, stars, galaxies, and a mist of invisible dark matter that outweighs everything we can see. All that mass curves space-time slightly inward. Gravity is simply the result of following the shortest path across that curved surface, what physicists call a geodesic. Light itself bends along these paths, which is why a distant galaxy can appear distorted when its light passes near another. The geometry of space, in that sense, is like a lens the universe uses to look at itself. Now, if we were to zoom out, far beyond galaxies, beyond clusters, into the largest scales we can imagine, we might ask, what kind of curve does the universe have overall? The possibilities are threefold, and each one paints a very different picture. In one version, the cosmos has positive curvature, like the surface of a sphere. Imagine ants walking on a globe. They think they're moving in straight lines, yet eventually they find themselves circling back to where they began. A universe like this would be finite but without edges, a closed world where space loops in on itself. In the second version, space has negative curvature, like the surface of a saddle. Here, parallel lines spread apart forever, and the geometry is open, infinite, and ever diverging. In the third, the universe is flat, neither curving inward nor outward. Distances add up exactly as they do on a sheet of paper, and parallel lines remain parallel forever. These are not artistic guesses. They arise naturally from Einstein's field equations, the same ones Lemaitre used when he first imagined the universe expanding. Translated softly, those equations tell us that the curvature of space depends on how much matter and energy the universe contains. If the total density is greater than a certain critical value, gravity wins and the universe curves inward like a sphere. If it's less, space curves outward like a saddle. And if the density is just right, balanced perfectly between the two, space remains flat. It's like balancing a pencil on its tip. Too much or too little mass, and the geometry tips one way or the other. But how can we know which of these describes our universe? The answer comes from light itself. When light travels through curved space, its path and apparent brightness change in predictable ways. By comparing the apparent size of distant features like the faint ripples in the cosmic microwave background, scientists can measure how much the light has been stretched or squeezed by curvature. The results so far are astonishingly precise. Within the limits of our observations, the universe appears to be flat. Also nearly flat that its curvature, if it exists, must be extremely gentle. To say the universe is flat does not mean it's like a tabletop floating in nothing. It means that on the largest scales, geometry behaves in the simplest possible way. Triangles add up to 180 degrees, parallel beams of light never meet, and the laws of physics remain uniform everywhere. The cosmic fabric, though vast and alive, is almost perfectly balanced between expansion and gravity. It's a kind of geometric grace, a universe poised on the fine line between falling back on itself and flying apart too fast. There's a quiet irony in this balance. The equation suggests that this perfect flatness should be unstable, like a ball balanced on a hilltop. The slightest deviation at the beginning of time would have magnified over billions of years, producing a universe wildly curved one way or the other. And yet, here we are, living in a cosmos that seems miraculously flat. To explain this, physicists propose a process called cosmic inflation, a brief, furious stretching in the first instant after the universe's birth. In less than a heartbeat, space expanded exponentially, smoothing out any irregularities. It was as though the universe ironed itself flat before continuing its slower expansion. We'll return to that strange moment later, but for now it's enough to know that the flatness we observe today is one of its quiet legacies. Even in a flat universe, the geometry of expansion can still surprise us. Distances themselves are not as simple as they seem. In an expanding cosmos, the meaning of far away depends on when you measure it. Two galaxies that are now 10 billion light-years apart might have been only a fraction of that distance when the light we now see first left them. Because space expands while the light travels, the light covers a longer path than you might expect. This is why astronomers talk about look-back time, the idea that distance and time are inseparable when we peer into the cosmos. Every direction is not just a direction in space, but a direction in history. To imagine this, picture a map that changes while you walk across it. The farther you go, the more the map stretches beneath your feet. If you drop a trail of pebbles behind you, you'll find that the spaces between them grow larger the longer you wait. That's what light experiences as it moves through expanding space. The geometry of the universe keeps rewriting the distances as the journey unfolds. Another way to picture this is through an ancient traveller's parable. Suppose you set sail on an endless sea, always moving straight ahead. If the universe is positively curved, you might eventually find yourself returning to your starting point. If it's negatively curved, your route will diverge endlessly, and your compass lines will never meet. If it's flat, you'll keep sailing forever in the same direction, never looping back but never escaping either. Each version feels infinite in its own way, one because it's truly boundless, another because it folds in on itself. To live in any of them is to inhabit infinity differently. Our measurements suggest that space is flat, yet we must speak carefully. The visible universe, the part we can see, might be flat like a small patch of an enormous sphere. Just as the Earth looks flat to someone walking on it, the cosmos may only appear so because we can't see far enough to detect its full curvature. The truth could be grander and subtler than our instruments can reveal. The cosmos might loop in ways we can't yet imagine, its geometry wrapping around like a hidden melody whose final note is still beyond hearing. And so, when we speak of the geometry of expansion, we are not talking about lines and circles, but about the soul of the universe, its natural shape, its quiet balance between gravity and flight. That shape determines everything: how galaxies form, how light travels, how time itself flows. The flatness we observe today allows the universe to keep expanding gently, neither collapsing into darkness nor tearing itself apart too soon. It is a fragile equilibrium, and perhaps a temporary one. If we follow the path of this geometry a little further, we begin to see the next layer of mystery. For even though the universe's shape seems calm, its motion is not. The expansion is speeding up, as though some invisible hand is pressing outward on the fabric of space itself. What could cause such a thing? Gravity pulls, it never pushes, and yet the cosmos is being pushed apart faster than before. To understand that, we must turn to the strangest idea of all, a form of energy that lives in emptiness, unseen and relentless, driving the expansion onward into the dark. For most of the 20th century, scientists believed that the universe should be slowing down. Gravity, after all, is the great reconciler, the quiet pull that draws everything together. It binds galaxies into clusters, holds planets in orbit, and keeps your feet pressed to the floor. The logic seemed inescapable. If the universe began in an explosive expansion, then over billions of years, gravity should have been tugging on that motion, gradually easing its speed. Like a ball thrown upward, the universe might rise for a time, then halt, and perhaps one day fall back inward toward a final collapse, the so-called Big Crunch. That was the expectation. An orderly cosmic arc from birth to stillness, expansion to return. But the universe, it seems, had other plans. In the late 1990s, two independent teams of astronomers set out to measure exactly how quickly the expansion was slowing. They didn't expect surprises, only precision. To do this, they looked for a kind of celestial candle, the explosions of dying stars known as Type Ia supernovae. These rare events happen when a white dwarf, a star's compact remnant, steals matter from a companion until it crosses a precise threshold and ignites in a thermonuclear blaze. Because that threshold is always nearly the same, every such supernova shines with roughly equal brightness. If you know how bright it truly is, then by measuring how faint it appears, you can calculate its distance, just as you can guess how far away a streetlight is by how dim it looks through the fog. These explosions, scattered across billions of light years, became the universe's mile markers. By comparing their distances to how much their light had been stretched, their redshifts, astronomers could chart how the expansion rate changed over time. If gravity was indeed slowing the expansion, then the most distant, oldest supernovae should appear brighter than expected, because in the past the universe would have been expanding faster and their light would have reached us more easily. But when the data came in, it told a story no one expected. The distant supernovae were dimmer, not brighter. Their light was weaker than it should have been, as though the galaxies that hosted them had drifted farther away than gravity alone could explain. At first, the researchers suspected an error. Perhaps cosmic dust was scattering the light, or maybe the stars weren't as uniform as assumed. But after years of careful cross-checks, the conclusion grew impossible to ignore. The expansion of the universe was not slowing down. It was speeding up. The cosmos, rather than falling under gravity's spell, was accelerating outward, as if some unseen hand were pushing on the fabric of space itself. The two research groups, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, announced their findings in 1998. It was one of those moments in science when the universe seems to turn around and whisper, "Everything you thought you knew is only half the story." The discovery landed gently, almost shyly, but its implications were seismic. Something was counteracting gravity, spreading galaxies apart faster and faster. That something was soon given a name: dark energy, not because it was black or sinister, but because it was unknown. It wasn't matter, it wasn't radiation, and it couldn't be seen or touched. It was a form of energy built into the vacuum of space itself, a kind of pressure that increases as space expands. The more room there is, the more of it appears. In effect, the universe creates more of its own fuel as it grows. If this sounds paradoxical, that's because it is. In Einstein's equations, energy and space are bound together. You can't have one without the other. If space expands, then the energy within it must expand too. Dark energy acts like a negative form of gravity. Instead of pulling things together, it pushes them apart. The greater the distance between galaxies, the stronger this push becomes. It's as though the universe is not only breathing out, but learning to exhale faster with every breath. To picture it, imagine a sailboat gliding across a calm sea, its sails filled not with wind, but with emptiness. At first, the boat drifts slowly, moved by the faintest pressure of that invisible breeze. But as the sea widens, the emptiness grows more insistent, pushing harder, swelling the sails until the boat begins to race. Galaxies are those boats, and dark energy is the silent wind filling their sails. It is everywhere, constant and invisible, a force without a source, a whisper without a speaker. Astronomers began to weave this discovery into the broader cosmic story. The universe, they realized, could be divided roughly into 3 ingredients. About 5% of it is ordinary matter, the atoms that make up stars, planets, and people. About 25% is dark matter, unseen mass that holds galaxies together through its gravity but does not shine. And the remaining 70%, the dominant portion, is dark energy, the mysterious something that drives the acceleration. In other words, most of the universe is made of things we do not understand. We live in the thin, bright foam atop a vast sea of the unknown. Even more curious, the numbers suggest that dark energy has only recently come to dominate. For billions of years after the Big Bang, matter ruled. Galaxies formed, stars ignited, gravity built the architecture of the cosmos. But as space expanded, matter grew thinner and weaker, while dark energy, which does not dilute, stayed constant. Eventually, the two forces reached a balance point. After that, dark energy began to win, and the universe's expansion started to speed up. We live in the epoch where that transition has just taken hold, a moment when gravity's long-reigning influence is quietly giving way to the power of emptiness. No one knows why the balance changed exactly when it did, or what it means for the future. If the current trend continues, galaxies beyond our local group will drift farther and farther away until their light fades beyond detection. The night sky would grow emptier over cosmic time, its stars thinning like dust in an ever-expanding room. Far in the future, distant galaxies might vanish entirely, their light stretched beyond all wavelengths we can see. The universe would appear still again, not because it stopped, but because it has carried everything beyond our sight. When scientists first proposed dark energy, it seemed absurd. But then they remembered something strange from Einstein's own work. In 1917, he had inserted a term into his equations to keep the universe static, a small, finely tuned value he called the cosmological constant. When Hubble later discovered that the universe was expanding, Einstein regretted that addition, calling it his greatest blunder. But decades after his death, it appeared that his blunder might have been prophecy. The cosmological constant describes exactly the kind of energy that could cause accelerated expansion, a constant pressure woven into the fabric of space itself. Perhaps Einstein had glimpsed the truth, but could not yet accept it. Even now, dark energy remains more a question than an answer. We cannot see it, measure it directly, or bottle it in a laboratory. We know only its effect: galaxies receding, the expansion speeding up, the cosmic wind blowing stronger each year. And yet, this invisible force defines the fate of everything. Gravity builds the universe, but dark energy decides its future. If the balance between them ever shifts again, the story could change entirely. From endless expansion to sudden collapse, or even to a catastrophic unbinding where every atom is torn apart. For now, though, the acceleration continues, quiet and steady. Space itself is stretching faster than ever before. It is as if the universe, once young and full of gravity's restraint, has grown restless, an ancient being rediscovering the urge to wander, and so it drifts outward, faster with every breath, guided by a wind we cannot see or touch. Our quiet exploration now turns toward that wind, the invisible pressure itself. What could it be made of? A fixed property of space, a quantum sea bubbling beneath reality, or something entirely new? A field still evolving with time? To find out, we must listen closely to the whispers of nothingness. What is this invisible wind that fills the universe? This quiet pressure that pushes galaxies apart and makes the stars themselves drift towards silence. We call it dark energy, but that name hides more than it reveals. Dark only means we cannot see it, and energy only means it does work, that it moves, expands, creates space. Beyond that, we know almost nothing, and yet, that almost nothing governs the destiny of everything. To understand it, scientists have proposed three main possibilities, three faces of the unknown. Each one is an attempt to capture the same mysterious truth, that emptiness itself might be alive. The first idea is the simplest, and, in some ways, the most elegant. It says that dark energy is simply a property of space itself, a built-in feature of the cosmic fabric. This is what Einstein once called the cosmological constant. You can imagine it as a faint tension woven through every thread of the universe, a kind of quiet pressure that never changes. Wherever there is space, there is this energy, always the same, never stronger or weaker. It doesn't matter how large the universe becomes, the vacuum's energy per volume stays constant. And because space keeps expanding, there is always more of it. The total energy of emptiness grows, and with it the speed of expansion. In this view, the universe is like a breathing balloon with air that cannot thin out. The more you stretch it, the more air there seems to be. The vacuum of space itself contains energy, even when no particles are present. It's not nothing. It's a sea of potential, a still ocean that never runs dry. But this idea, while beautiful, leads to a riddle. When physicists try to calculate how much energy the vacuum should contain, using the rules of quantum mechanics, they get a number that is almost unimaginably too large, about one followed by 120 zeros times the amount we actually observe. To say it softly, that's a mismatch so extreme that if those equations were right, the universe would have blown itself apart before it ever had time to form stars. Somehow, nature cancels almost all of that energy, leaving behind only a whisper of what the math predicts. Why? No one knows. It is the most precise coincidence, or the most delicate balance, ever found in physics. So perhaps the cosmological constant is not the whole story. Maybe the energy of the vacuum is not perfectly constant after all. Maybe it changes slowly and subtly as the universe expands. That idea leads to the second face of dark energy, the quantum vacuum itself filled with restless activity. In quantum physics, even empty space is never truly empty. Tiny particles and antiparticles flicker in and out of existence, borrowing energy for a brief instant before vanishing again. This shimmering foam of creation and annihilation happens everywhere, all the time, at every scale. Each of these flickers leaves behind a faint pressure, an echo of existence. When you add up all those whispers, you get a kind of background hum that fills the universe. This quantum hum might be what we experience as dark energy, Not a fixed constant, but a living process of continual birth and disappearance. To imagine it more softly, picture the surface of a calm lake under moonlight. To your eye, it looks still, but if you kneel closer, you'll see the tiniest ripples moving across it, ripples that never rest. The universe's vacuum is like that lake, calm from a distance but trembling underneath, and it's those invisible ripples, multiplied across infinite space, that may be pushing everything apart. The third possibility is more adventurous still. What if dark energy is not a property of space or the quantum vacuum, but a field? Something dynamic, evolving with time, much like a weather system spread across the universe. Physicists call this idea quintessence, borrowing the ancient word for the fifth element, the mysterious substance once believed to fill the heavens. Quintessence would be like a cosmic fluid that ebbs and flows, sometimes stronger, sometimes weaker, as the universe grows. Its pressure could vary, its influence could change, perhaps even reverse someday. If that were true, dark energy might not last forever. Acceleration could slow, stop, or even turn into contraction again in the far future. Quintessence makes the universe more alive, less mechanical. In this version of reality, expansion isn't a fixed rule written once and for all. It's a phase, a moment in the cosmic story. Just as seasons change on Earth, the universe might pass through stages of expansion and stillness, each governed by how this invisible field behaves. Somewhere deep in its equations, time itself could carry a heartbeat. No matter which idea is right, the constant, the quantum foam, or the evolving field, all three raise the same question. Why now? Why, out of all the billions of years since the beginning, is dark energy dominating today? For most of cosmic history, matter was stronger. Galaxies grew, stars formed, gravity ruled. But now, in the present era, dark energy has taken over, pushing matter aside like a tide overtaking the shore. It's as if we arrive just in time to witness a delicate turning point, the moment when gravity yields to emptiness. Scientists have tried to find meaning in that coincidence, but so far none fits comfortably. Some suggest that perhaps we could only have arisen in an epoch like this, one balanced enough for galaxies to exist but not yet so empty that stars have faded. Others whisper that maybe this balance isn't coincidence at all, maybe countless universes exist, each with different mixtures of matter and dark energy, and we just happen to live in the one where the numbers make life possible. But those are speculations, gentle guesses about possibilities that may never be proven. Still, these three faces of the unknown, constant, quantum, and evolving, give us a framework to imagine how the universe's breath might continue. If the cosmological constant rules, expansion will go on forever, gently accelerating until galaxies vanish beyond reach. If the quantum vacuum dominates, there might be fluctuations, waves of faster or slower expansion, the universe pulsing subtly across eons. And if quintessence is true, the cosmos could one day change direction, its outward rush slowing, pausing, perhaps even folding back inward. Each possibility writes a different ending to the story of time, yet, through all this uncertainty, one truth remains quietly clear. Whatever dark energy is, it's not an intruder. It's part of the same fabric as light and matter and gravity. It's the other side of the same coin, the yin to gravity's yang. Gravity gathers, dark energy disperses. One pulls things together, the other gives them room to exist. Without gravity, there would be no stars. Without dark energy, there might be no vast open sky to hold them. The more we learn, the more the universe seems to balance opposites with extraordinary grace. Contraction and expansion, attraction and release, being and nothingness. Perhaps dark energy is simply the cosmos's way of keeping its own tension, a gentle reminder that even emptiness has a role to play. As we drift further into the story, we'll begin to see how these invisible forces shape not only the motion of galaxies, but the geometry of the universe itself, how its shape decides its fate, and how even flatness hides the potential for endless surprises. If the universe is a story written in the language of geometry, then its ending depends on the shape of its lines. The way space bends, curves, or stays flat determines not only how light travels, but how the future unfolds. The cosmic expansion may be guided by mysterious energy, but it is shaped, literally, by the structure of space-time itself. To understand how everything might end, we must first understand how space is built. Imagine holding a sheet of paper. If you draw two straight lines side by side, they never meet. This is what we call flat geometry. Simple, familiar, like the floors and walls of the world we know. But bend the paper gently into a sphere, and the lines, if extended long enough, will meet at the top, just like lines of longitude converging at Earth's poles. That is positive curvature. If instead you pull the paper outward, curving it like a saddle, the lines will diverge endlessly, never meeting at all. That is negative curvature. These three forms, flat, closed and open, are the only ways space can bend on a grand scale. Each one writes a different destiny for the universe. In a closed universe, space curves back on itself, like the surface of a globe. Travel far enough in one direction, and you could, in theory, return to where you started. Such a universe is finite but without edges. No walls, no borders, just a continuous looping of space. If gravity and matter outweigh the push of expansion, this closed universe could one day stop growing and begin to contract. Galaxies would slow, halt, and fall back inward, their light reddening as they move through the final act of cosmic collapse. Eventually, everything would merge again in a brilliant reversal of the Big Bang, a fiery big crunch where time itself might fold. In an open universe, the opposite is true. Space curves outward, saddle-shaped and infinite. Parallel lines spread apart, triangles sum to less than 180 degrees. Distances stretch faster than they can ever close. In this geometry, gravity never gains the upper hand. The universe expands forever, but more and more slowly. Galaxies drift farther apart, their light fading until even the nearest neighbour becomes invisible. It's a cold, lonely fate. The cosmos is an endless desert, still growing but losing all memory of warmth. Between these two lies the most delicate of possibilities, a flat universe. Here, the curvature is perfectly balanced, neither curling inward nor arching outward. Parallel lines remain forever parallel. The sum of the angles in a triangle is exactly 180 degrees. This is the geometry our measurements suggest most closely matches reality. It's not curved like a globe, not bent like a saddle, but stretched smooth, like an infinite calm sea. The balance between matter, gravity, and expansion is so precise that even the smallest deviation, just a fraction of a percent, would have tilted the outcome. And yet, somehow, the universe walks that line. Physicists sometimes describe this balance as a kind of cosmic mood. A closed universe is intimate and self-contained, like a room with softly curving walls. An open universe is restless and unbound, like a vast windswept plain. A flat universe is tranquil, endless, poised, and eerily stable. Each mood arises from the same fundamental rules, just tuned differently by the contents of the cosmos. Matter and energy act as sculptors, carving the curvature through their combined gravity. The more mass there is, the more the fabric bends inward. The less, the more it stretches outward. There exists a special value, a just right density, where the two perfectly cancel, producing flatness. Scientists call it the critical density, but we can think of it more softly as the balance point of creation. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, allow us to measure this balance with remarkable precision. The light from that ancient time carries patterns, ripples frozen in space when the universe was young. By studying how those ripples appear stretched or compressed, astronomers can deduce the geometry of the universe. And what they've found is astonishing. The cosmos appears flat to within less than a single percent. The great cosmic sea seems to go on without curvature as far as we can see. But this raises a quiet question. Perfect flatness is unstable. Like a coin balanced on its edge, even the slightest tilt should have sent the universe curving one way or the other. For it to remain so balanced after billions of years suggests something extraordinary happened at the beginning. Some early process, an enormous burst of inflation, must have stretched space so quickly that any curvature was ironed out, leaving behind a flat, nearly featureless expanse. We'll return to that idea soon. For now, we can simply marvel that the geometry of everything seems so delicately poised. In practical terms, this geometry also decides the universe's fate. In a closed world, expansion might slow, halt, and reverse, ending in a brilliant collapse. In an open or flat world dominated by dark energy, expansion continues forever, though with differing tempers. If dark energy remains constant, the cosmos will drift toward a big freeze, galaxies separating beyond reach, stars burning out, and even atoms eventually dissolving into the chill of eternal night. If dark energy grows stronger, the universe could face a more violent future, a big rip, where even galaxies, planets, and molecules are torn apart by the accelerating stretch of space itself. And if dark energy fades, expansion might someday stall, leaving the universe to coast in a quiet twilight, neither expanding nor collapsing, like a breath held between inhale and exhale. Each of these outcomes, crunch, freeze, rip, or stillness, is written in the same geometry we see today. It's not only about what the universe contains, but about how it is shaped. Geometry is destiny. A small shift in curvature, a slight change in the pressure of dark energy, and the entire story bends differently. For now, all signs point to an ever-expanding, nearly flat cosmos driven by a steady dark energy. That means our universe is likely headed toward the big freeze, a slow, graceful fading rather than a cataclysm. Over trillions of years, stars will burn their last fuel, galaxies will drift into darkness, and the night sky will empty. Yet even that distant future has a quiet elegance. The universe, in its old age, will grow more peaceful, more uniform, more still. Its temperature will approach absolute zero, its light will fade to invisibility, but its geometry will remain perfect, the calm sea stretching forever. And yet, even perfect flatness may hide deeper secrets. The universe could appear flat locally but still loop back on itself in ways we cannot yet perceive. Just as Earth seems flat to someone walking across its surface, the cosmos might be finite but unbounded, a shape that connects to itself in higher dimensions. If that's true, then somewhere out there, light from our own galaxy could one day circle back, arriving again from the other side. The idea sounds fantastical, but it's not impossible. Space may be cleverer than our senses allow. The thought brings a strange comfort. Whether open or closed, flat or curved, the universe continues to expand, a dance between gravity's pull and dark energy's push, written into the very geometry of existence. We don't yet know which note will end the song, but we can feel its rhythm in every star, every beam of redshifted light, every quiet breath of space. From here, the story bends gently into something even more mysterious. For if space might fold back on itself, perhaps infinity is not as endless as it seems. Perhaps we're already travelling through echoes of our own past, unknowingly looking across the sky at light that has circled the cosmos and returned. The shape of the universe decides its fate, but its topology, its hidden loops and folds, may decide what infinite truly means. Infinity is one of those words that feels simple until you try to picture it. We imagine it as endlessness, a road that stretches forever, a sky that never stops. But the truth might be more intricate than that. The universe could be infinite extent, yes, but it could also be finite and still without edges. It might loop back on itself, quietly folding space in ways that defy ordinary intuition. To understand this, we have to think not about size, but about connection, about how space might join itself in hidden ways, forming a cosmic labyrinth where straight lines don't always stay straight, and travelling far enough could one day bring you home. When we say the universe is flat, we mean that it follows the simple rules of Euclid, the same geometry you learned in school. Parallel lines never meet, and triangles add up neatly to 180 degrees. But flatness doesn't necessarily mean endless. There are flat shapes that are finite too, like a video game world that wraps around when you walk off one side of the screen and reappear on the other. Mathematicians call such spaces topologically closed, meaning they connect to themselves in higher dimensions. In these universes, you could travel straight forever without ever finding an edge and still return to your starting point. The simplest example is something called a 3 torus, the three-dimensional equivalent of a donut surface. Imagine space like that. If you move far enough in one direction, you emerge from the opposite side, not because you turned, but because the universe itself curved around. Every direction loops, every path eventually closes. To an observer inside, it feels infinite, because there's no wall, no border, nothing to tell you that you've come full circle. Yet from a higher dimensional perspective, it's all self-contained, a single continuous whole. You can think of it this way. The universe could be a hall of mirrors so vast that you don't notice the reflections. Light leaving your galaxy might wrap around the cosmos and return from the opposite direction billions of years later, showing you an image of your own Milky Way in its youth. It's a haunting idea that the night sky could contain multiple reflections of the same galaxies, seen at different times. You might be staring at the early universe, but also at yourself many billions of years removed. Scientists have actually looked for these repeating patterns, signatures that might reveal such loops. They search the cosmic microwave background, that ancient afterglow of the Big Bang, for matched circles, regions of identical temperature variations that would indicate the light has wrapped around and overlapped itself. So far, no perfect matches have been found, but the search continues. The universe might be too large for the light to have completed a full circuit yet. Or perhaps the topology is more complicated, twisted in ways beyond our current models. One such possibility is a shape known as the Hantscher-Wendt manifold, a space that loops back on itself but also flips and twists in the process. You could travel in a straight line, return to your starting point, and yet find that everything is mirrored, reversed, as though you had crossed into a reflection of the universe. If that sounds like something from a dream, it's because these shapes stretch the limits of imagination. They exist comfortably in mathematics, but in the human mind they feel like paradoxes, infinity that fits inside itself. The beauty of these models is that they preserve the elegance of flat geometry while giving the cosmos a kind of hidden intimacy. In a finite but unbounded universe, there are no edges, no borders where things stop. Everything connects, and distance becomes cyclical rather than absolute. If you could somehow trace a straight beam of light across such a cosmos and wait long enough, far, far longer than the universe's current age, that beam might eventually return to its origin, carrying with it the memory of its own journey. This idea changes how we think about infinity. It suggests that the universe could be both endless and contained, both vast and familiar, like walking through a forest at night and realizing that every path leads somehow back to the same clearing. The illusion of endlessness comes not from size, but from repetition, from the way space reuses itself. And if the universe really does loop, then the sky we see tonight might be showing us echoes of its own structure, faint symmetries written in the background light. The patterns in the CMB, those subtle temperature ripples we can still measure today, might hold whispers of that global geometry. Some regions of the sky seem almost to rhyme with others, like verses repeating with small variations. Whether these are artifacts of noise or genuine fingerprints of topology, no one yet knows. Even if space doesn't close in this way, the possibility reshapes how we think about our place in it. It reminds us that infinity isn't about size, it's about continuity. The universe could be as large as it wants, but if it folds, connects, or mirrors itself, then the concept of edge loses meaning. There's nowhere to fall off, nowhere to escape, not because the universe traps us, but because it contains all directions within itself. It also reframes a question as old as philosophy itself. When we look outward, are we really just looking inward? In a looping universe, that might be literally true. Every line we draw into space eventually curves back. Every question we ask about what lies beyond eventually points home. The cosmos becomes not a vast emptiness, but a single, unbroken surface of being, endlessly exploring itself. This possibility doesn't make the universe smaller, it makes it more intimate. Every star, every atom, every photon would be part of one continuous whole, bound not by walls but by connection. The expansion we've spoken of, the growing of space, as would not be an opening into emptiness, but an unfolding within itself. Each moment of growth would add depth, not distance, like a melody finding new harmonies without ever leaving its key. If someday we confirm that the universe truly wraps around, it would mean that the edge of discovery lies not at the horizon, but within the patterns of light that already surround us. Perhaps we've already seen our own cosmic reflection without realizing it, a faint duplicate of the Milky Way flickering in the depths of space, separated from us not by distance, but by time's long loop. And if that's true, then infinity isn't cold or unreachable. It's warm, recursive and close, a kind of cosmic homecoming. Every step outward becomes a step inward. Every direction eventually leads back to where we began. As we follow this quiet thread into the next part of our journey, we'll leave geometry and topology behind and step gently into philosophy, to the edge that isn't really an edge, the horizon that moves as we move. We'll look beyond the boundaries of what we can see and ask, what lies past the limits of our cosmic vision, and why can't we ever quite reach it? When you look up at the night sky, you are gazing into a vast ocean of time. Each point of light is not just far away in space, it is far away in age. Some of the stars you see tonight might already be gone, their light still crossing the long bridge between what was and what is. The farther you look, the older the universe becomes, until eventually you reach a limit, a horizon beyond which light has not yet had time to arrive. That edge is not the edge of the universe, it's the edge of what we can see, the limit drawn by the finite speed of light and the finite age of time itself. Astronomers call this the observable universe, a sphere centered on every observer. It's about 46 billion light-years in every direction from where we stand, a radius so large that even the word distance begins to lose meaning. We can't step across it, or even truly picture it, but we can describe it. It's not a physical wall, not a barrier of matter or light, but a horizon made of time. Beyond it, the universe continues, perhaps infinitely, perhaps folding in on itself. But we will never see it, because its light hasn't yet reached us, and in many cases, it never will. To understand this, imagine standing on a foggy plain. You can see only as far as the mist allows. Beyond that, you know the landscape continues, but it vanishes into whiteness. That's what our cosmic horizon is like. The fog in this case isn't vapor, it's time. Light travels at a finite speed, 300,000 kilometers each second, but space itself is expanding as that light moves. The expansion stretches the road beneath the light's feet, so that even though the beam races forward, the finish line keeps receding. There are regions of the universe whose light will never reach us, no matter how long we wait, because the space between grows faster than light can cross it. Those places aren't outside the universe, they're simply beyond our reach. This means that what we call the universe is really a bubble of visibility, a sphere of light centered on us. But every observer, on every planet, in every galaxy, sees a similar bubble centered on themselves. The universe has no single center. It's like a loaf of bread filled with raisins, each raisin seeing the others drift away but always feeling at the middle of the dough. Our observable universe is one raisin's view of the loaf, a window cut into a much larger unseen hole. If we could somehow pause time and look around, the horizon would be our cosmic shoreline. Beyond it lies the rest of the universe, regions forever hidden from view. Yet, strangely, the boundary isn't fixed. As time passes, light from more distant galaxies reaches us, and our horizon expands. The universe is revealing itself slowly, like dawn creeping across an endless landscape. Every day our visible sphere grows, not because we move, but because light does. We're constantly receiving messages from deeper layers of the past, new galaxies, new memories, new chapters of the cosmic story. But there's a catch. While the observable universe grows, the galaxies within it move farther apart. Some of them cross what's called the cosmic event horizon, the point beyond which even light emitted today will never reach us in the future. It's a boundary defined not by where things are now, but by how fast space itself is stretching. As dark energy drives acceleration, more and more galaxies will slip beyond that horizon. Their light will fade, redshift into invisibility, and eventually vanish from the cosmic stage. One day, billions of years from now, the night sky might hold only the faint glow of our local cluster, all else gone beyond recall. You could say that our horizon is both a gift and a reminder. It shows us how far we've come in understanding, but also how limited we still are. No matter how powerful our telescopes become, no matter how long we wait, there will always be a veil, a region of the universe that remains forever hidden. It's not because it doesn't exist, but because light, patient as it is, cannot outpace the expansion of space. The universe keeps the farthest parts of itself secret, as if reminding us that mystery, too, is part of its design. Think of it like being at sea, standing on the deck of a ship. The ocean surrounds you, unbroken, but the horizon always lies the same distance away. Sail as far as you wish, and the line only moves with you. It's not a real edge. It's a limit of sight set by the curvature of the world and the finiteness of vision. The universe behaves in the same way. The more we learn, the more we realize that our horizons, scientific, cosmic, even human, expand only to reveal new ones beyond them. To put the scale in human words, when we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. The light began its journey before Earth had oceans or continents. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we're seeing the universe as it was only 380,000 years after its birth. Beyond that, light could not yet travel freely. The universe was too dense, too hot, too foggy with ionized matter. That ancient radiation forms the ultimate limit of sight, the farthest wall of our visible bubble. It's not an edge of space, but the edge of time as light can carry it. This concept bends the mind in quiet ways. The observable universe is not a place. It's an experience of light. It's everything the universe has allowed us to see so far. And because the universe is expanding faster than we can explore, our view of it will never be complete. We're like people living in a room whose walls slowly recede, revealing new corners even as others fade into shadow. What we can observe is a conversation between light and time, and we happen to exist at a moment when that conversation is rich and full of voices. Someday, long after humanity is gone, if some future observer in another galaxy looks at the night sky, they may see almost nothing beyond their own cosmic island. The evidence of the Big Bang, the redshift of galaxies, the afterglow of creation, all of it will be gone, carried beyond their event horizon. Their universe will appear quiet and eternal, static and cold. They will have no way to know that it was once alive with expansion. We live in a rare window of cosmic history, a brief era when the universe still tells its story through light. And that story carries a quiet truth. Horizons are not walls, they're invitations. They remind us that seeing farther doesn't mean reaching the end, it means discovering new beginnings. The universe may have boundaries of observation, but it has no boundaries of being. What lies beyond our horizon isn't emptiness, it's simply tomorrow's light still on its way. As we drift gently further, the question deepens. If we live inside an expanding universe with no edge, and if beyond every horizon more space waits unseen, how can something already infinite still grow? What does it mean for infinity to expand? The paradox is subtle, but it carries us to the heart of the next mystery, the nature of boundlessness itself. Infinity is one of those ideas that hides in plain sight. You can say the word easily enough, but if you try to imagine it, your mind begins to slide. A road that never ends, a sea without shores, a sky that goes on forever. Every image eventually collapses under its own weight. We live surrounded by limits, of sight, of time, of strength. So when science tells us that the universe may be infinite, we nod politely, but we don't really feel it. The imagination simply doesn't have enough room, and yet infinity is everywhere in the language of cosmology. It's in the equations that describe space, in the stretch of light across the void, and in the very question of how something that is already endless can still be expanding. To understand this gentle contradiction, we must remember that expansion in cosmology does not mean adding more space to the outside. There is no outside. Instead, expansion means that the distances between things within the universe are increasing. The space between galaxies, between clusters, between the great filaments of matter that form the cosmic web. If the universe is infinite now, it was infinite before. The expansion doesn't make it more infinite, it simply changes the scale. Every distance doubles, every wavelength lengthens, every measure of time grows, but infinity stays infinity. You can multiply endlessness by any number, and it is still endless. Expansion, then, is not about size, it's about proportion, the quiet swelling of the cosmic fabric without changing its fundamental boundlessness. A simple way to picture this is with a grid drawn on a balloon. As the balloon inflates, each square on the grid stretches, and the distance between points grows, but there is no new square added at the edge. The whole pattern just becomes larger. Now imagine a balloon so vast that it has no surface, no edges at all. Every part of it expands, yet there is nowhere for it to expand into. That is our universe, a boundless geometry whose expansion is internal, not external. This means that even if the universe is infinite, it can still have motion. Infinity is not a fixed thing, not a static concept frozen in perfection. It can breathe, it can evolve. When cosmologists say the universe expands, they are describing how that infinite fabric changes its rhythm, how the spacing of its threads grows with time. The pattern stays the same, but the scale of the weave increases. The distances between galaxies grow like the spacing between notes in a song slowing down. The melody continues, but its tempo stretches, and yet there's another layer to this paradox, one that feels less mathematical and more emotional. If the universe is truly infinite, then somewhere out there, every possible arrangement of matter must occur. Not once, but endlessly. The atoms that make you, the pattern of your thoughts, the shape of the trees outside your window, all of it, if the laws of physics are uniform, must repeat in some distant region, so far away that its light will never reach us. Somewhere in that unreachable expanse, another version of you may be listening to these same words, wondering the same thing. Not a science fiction twin, but a statistical inevitability, a reflection written by infinity itself. The thought can be unsettling or comforting depending on how you hold it. It means that nothing is entirely unique, and yet, in another sense, everything is eternal. Every story ever told, every dream ever dreamed, repeats endlessly across the infinite cosmos, scattered like stars, each version unaware of the others, each carrying on its quiet life, like notes echoing in a hall so large that no sound can ever return. But infinity, even when it repeats, is not monotony, it's possibility. It ensures that every variation, every twist of probability can exist somewhere. Some universes might have different histories, others might never form stars at all. Infinity is a promise that the cosmos never runs out of imagination. It's the guarantee that creation never reaches the end of its page. Mathematically, infinity is tricky. When scientists describe the universe, they don't truly calculate infinity. They describe how quantities behave as they grow without limit. It's an approach, not a destination. When we say the universe is infinite, we mean that space has no boundary where it ends. Not that it's literally filled with an endless count of things. The expansion we measure, expressed through what physicists call the scale factor, simply means that all distances grow in proportion. Every galaxy is farther from every other galaxy than it was before, and that ratio of separation increases over time. It's like watching the markings on a ruler stretch apart while the ruler itself stays perfectly whole. And even in this infinite stage, light still moves, matter still evolves, time still flows. Infinity doesn't mean frozen perfection. It means endless motion, endless change. The universe may have no edge, but it still has a history. It began from a hotter, denser state, and has been cooling ever since. Expansion doesn't make infinity larger, it makes infinity older. If we return to the paradox, how can something infinite still expand? The answer becomes softer. Expansion is not about more space, it's about the relationship between things. The universe doesn't grow into anything, it grows between everything. The galaxies drift apart, the light stretches, and the fabric of space-time thins like paint, brushed across an ever-widening canvas. Infinity isn't increasing, it's unfolding. And there's a deeper reflection within this. Even in an infinite universe, the parts of it we can see are always finite. Our observable horizon, that glowing sphere of ancient light, will always be limited by time and by the speed of light itself. No matter how vast infinity truly is, we'll only ever experience a fraction of it, and that's enough. Infinity doesn't need to be grasped to be real. Like music, it exists in the resonance between notes, not in the silence before or after them. So perhaps the most meaningful way to understand infinity is not as a number, but as a feeling. The sense that there is always more to learn, more to see, more to become. Just as the universe expands without edge, so does curiosity, consciousness, and wonder. Every question leads to another. Every horizon once reached reveals a new one beyond. In that sense, the infinite isn't out there, waiting to be measured. It's inside us, expressed in our endless urge to explore. Maybe that's the true paradox, that finite beings can sense the infinite, that small minds, bound by time, can look at a night sky and somehow feel eternity pressing gently against their hearts. It's not a contradiction. It's the same story written on two scales, one cosmic, one human. And so, as we drift gently forward, we leave infinity not as a solved riddle, but as a companion, a reminder that the universe may never end, but neither does our capacity for awe. From here, our attention turns from space to time itself, to the edge that isn't an edge, but a beginning woven into every direction. If the universe has no border, does it at least have a starting line? Or does time, too, curve back into itself just as space might? When people imagine the Big Bang, they often picture an explosion, a fiery burst in the middle of darkness, sending fragments of matter rushing outward into empty space. It's a natural image drawn from what we know of fireworks or storms or life itself beginning with motion. But the truth is far stranger and far more peaceful. The Big Bang wasn't an explosion in space, it was the birth of space itself. There was no centre, no outside, and no emptiness waiting to be filled. There was only everything, compressed into a state so dense and hot that time itself had barely begun to flow. The edge of the universe is not in distance, it's in time. To understand this, imagine the universe as a film playing in reverse. As you rewind, galaxies draw closer, stars grow younger, and the cosmic background light brightens and shifts from red to blue. Keep rewinding and the stars vanish, replaced by a uniform glow of energy. Continue further still, and even atoms come apart. Protons and neutrons melt into pure plasma. Rewind a little more, and the fabric of space itself becomes smaller, more curved, more compressed, until you reach a moment when the entire universe fits into a single, blazing point of light. That's the Big Bang. Not a location, but a time. The first frame of the cosmic movie. If we could somehow stand at that first instant, and of course we couldn't. There was no standing yet, no space to stand in. We would find no edge or boundary. Every point in space today was once part of that same dense beginning. The Big Bang happened everywhere at once. It wasn't a fireball expanding into the void. It was the void itself unfolding. Every place in the universe was that beginning. You carry it inside you. The atoms in your body, the air you breathe, the photons that warm your skin, all trace their lineage to that same moment. This also means that asking what came before the Big Bang may not make sense in the way we expect. Before time began, before had no meaning. The equations that describe space-time tell us that when you follow the cosmic clock backward, time doesn't extend forever. It curves gently toward a boundary, not a wall, but a smooth horizon where the concept of earlier simply dissolves. You can think of it like travelling to the North Pole. Once you arrive, there's no farther north to go. You're not at the edge of the world, but at the point where that direction stops existing. The beginning of time is like that, not a wall, but a turning point. In those earliest moments, everything we understand about physics begins to blur. Temperatures were so high that the known forces of nature, gravity, electromagnetism, and the two nuclear forces merged into one. Space and time may have been entangled in a single fluid dimension. Some theories suggest that what we call the Big Bang wasn't the start of everything, but rather a transition, a change in the state of the universe, perhaps from a previous phase of existence that we can no longer see. Others propose that time itself may be cyclical, curving back like a loop, so that the end of one universe becomes the birth of another. But even without such speculations, one thing is clear. The edge of time is real. We can see its faint trace in the sky every night, the afterglow of creation, the cosmic microwave background. That light, now stretched into invisible microwaves by billions of years of expansion, is the oldest thing we can observe. When we detect it, we're looking across nearly 14 billion years to the moment when the universe first became transparent, when light could travel freely through space. Beyond that point lies the true mystery, the opaque dawn, the place where our knowledge fades into silence. Einstein's equations, softly translated, tell us that space and time are intertwined. You cannot have one without the other. The shape of time depends on the energy and matter within space, and the shape of space depends on how time flows. When you approach the Big Bang, both space and time tighten like a knot. The closer you get, the faster everything moves, the hotter everything becomes, until our mathematics stops working. That breakdown isn't a failure of truth. It's a reminder that our language, even the language of physics, cannot yet describe the very beginning. Some cosmologists have tried to imagine what might exist beyond that boundary. One idea is that the universe could have emerged from a quantum fluctuation, a brief spark of energy that, instead of fading, expanded and cooled into the cosmos we know. Another suggests that our universe may have budded off from a larger multiverse, one bubble in a vast sea of space-time, each bubble with its own version of physics. And yet another theory proposes that time before the Big Bang flowed in the opposite direction, like a mirror image, a universe running backward, hidden from ours except at the point of contact, the moment we call the beginning. Each of these possibilities shares a quiet humility. We do not know what time itself truly is. We measure it, we feel it, but we don't yet understand its substance. We live inside it like fish inside water, surrounded, sustained, but never outside enough to see the whole ocean. If we could step outside time for a moment, we might see the universe as a complete sculpture, not beginning or ending, but existing all at once, a timeless structure with every moment laid out together. In that view, the Big Bang would not be the first point, but simply one part of the whole form, a region where the curve of time meets its origin. Perhaps the universe didn't begin so much as it is, a continuous object, self-contained and complete, like a sphere that has no edge but includes its own surface. What makes this idea so powerful is that it replaces chaos with continuity. Instead of a violent explosion, we have a graceful unfolding. Instead of a singular start, we have a transition from silence into motion, from potential into being. The Big Bang becomes not a bang, but a breath. The universe exhaling itself into existence. And that breath is still moving. Every photon in the sky, every vibration of space, carries the memory of that first expansion. The edge of time isn't just in the past, it's here, folded into every second we experience. Every tick of a clock is an echo of that first pulse, stretched thin but never lost. Time began everywhere, and it continues everywhere, quietly, ceaselessly, as the universe keeps expanding its own story. If you ever find yourself wondering where the universe ends, try looking not outward, but backward, not to the edges of space, but to the edges of time. There, in that first light, lies the boundary that defines everything else. It's not a wall, but a whisper, a point where the universe turned from silence to song. And as we follow this melody further, we'll see how that first instant may not have been the only beginning. For some physicists now believe that the Big Bang itself was sparked by a deeper event, a brief explosive stretch called inflation, where space expanded faster than light, smoothing and shaping everything that followed. It was the great stretch that turned chaos into cosmos, and it might still be happening, somewhere beyond our view. The early universe, as far as we can trace it, was astonishingly smooth. No direction appears special, no corner thicker or thinner, no region older or younger than another. The cosmic microwave background, that ancient afterglow we now capture, with radio telescopes, glows almost evenly across the sky, differing by no more than 1 part in 100,000. Yet that perfection poses a riddle. If light travels only so far in 14 billion years, then regions on opposite sides of the sky should never have been in contact. They should not have had time to share temperature, energy, or information. And still, they match. It's as if two strangers who never met somehow chose the same heartbeat. This puzzle, called the Horizon Problem, left cosmologists restless for decades. There were other mysteries too. Why the universe appears so flat, balanced so precisely between curvature and openness, when even a tiny deviation at the beginning should have amplified into something wildly different today. And why the cosmos didn't collapse under its own gravity the moment it began, or tear itself apart from the energy locked inside its newborn fabric. For all its beauty, the Big Bang model left these questions open until a bold idea arrived in the early 1980s, whispered from the mind of a physicist named Alan Guth. He called it inflation. In the softest terms, inflation suggests that during the universe's first fraction of a second, space itself expanded at an extraordinary rate. Not just fast, but unimaginably fast. In less than a trillionth of a second, the universe grew from smaller than an atom to something the size of a grapefruit or perhaps larger. The numbers are staggering, but we can translate them into feeling. Imagine watching a single bubble in boiling water, and before you can blink, that bubble becomes an ocean. That is what inflation did. It took the quantum seed of the cosmos and stretched it beyond all recognition. The cause of this expansion, according to the theory, was a peculiar form of energy trapped in a high state, something like tension stored in a coiled spring. When that energy finally released, space expanded faster than even light could cross. This doesn't break the rules of physics, because it wasn't matter moving through space at that speed. It was space itself expanding, carrying everything with it. The light was not outrun. The finish line simply receded. Inflation elegantly solved many of cosmology's riddles at once. The vast, smooth temperature of the universe. During that brief instant, everything was so close together that it could easily reach equilibrium before being blown apart by expansion. The flatness of space. Inflation stretched any initial curvature so wide that it became indistinguishable from flatness, much like how a small patch of a balloon's surface looks flat when viewed up close. The absence of relics, exotic particles predicted by earlier theories that we've never observed. Inflation diluted them, spreading them thin across the growing cosmos until they vanished from our view. But inflation did something even more profound. It planted the seeds of all future structure. Even before galaxies formed, the quantum vacuum was alive with tiny fluctuations, random jitters in energy that appear and vanish constantly at microscopic scales. Under normal circumstances, these fluctuations average out, leaving no lasting trace. But inflation changed that. It took those quantum ripples and stretched them across vast regions of space, freezing them into place. When the universe later cooled and matter began to gather, those faint variations became the blueprint for everything. The reason galaxies cluster as they do, the reason stars and planets formed at all. Every cosmic structure, from superclusters to grains of cosmic dust, can trace its origin to the smallest whispers of quantum uncertainty amplified by inflation. It's humbling to think that the same restless flicker that drives atoms to dance also sculpted the grand architecture of the cosmos. The large-scale map of galaxies we observe today, the filaments, the voids, the glowing threads that span hundreds of millions of light years, is like a magnified image of those primordial ripples. The pattern is cosmic handwriting, written before there were hands to read it. The mathematics behind inflation, when softened into words, says that the energy of this early vacuum acted like a repulsive form of gravity. Instead of pulling matter inward, it pushed space outward. You could think of it as gravity turned inside out, an anti-gravity that made the universe grow instead of shrink. When that stored energy finally decayed, it released a storm of particles and radiation, reheating the cosmos and continuing into the more familiar slower expansion we still observe today. And though inflation ended here, it may not have ended everywhere. Some versions of the theory predict that inflation never fully stops. It continues eternally in different regions, each giving birth to new bubble universes that grow and evolve independently. Our entire observable cosmos could be just one bubble in this infinite froth, floating among countless others, each with its own laws of physics, its own constants of nature, its own possibilities. In one, gravity might be stronger. In another, time might flow differently. It's a wild thought that creation never truly paused, but continues to bloom endlessly in places we'll never see. Yet even if we never confirm those distant bubbles, inflation's fingerprints remain all around us. The subtle patterns of temperature in the cosmic microwave background, measured with exquisite precision by satellites like Planck and WMAP, match the predictions beautifully. The tiny fluctuations, the same 1 in 100,000 variations we first noticed, are exactly the scale that inflation would have produced. It's as if the universe left a faint signature in the oldest light, a quiet acknowledgement that yes, it once stretched beyond imagination. Still, questions remain. What triggered inflation? What kind of field or energy caused it? And why did it stop? The physics behind it remains hidden, like a melody we can hum but not yet write down. Some suggest it was a scalar field, a gentle ocean of energy permeating space, called the inflaton. But no one has seen it. For now, inflation is both our best explanation and our greatest mystery. A story half told by the light itself. There's a quiet poetry in that. The universe began not with a bang, but with a stretch. A silent widening that smoothed chaos into calm and turned quantum trembling into the architecture of galaxies. It was not destruction, but release. Not noise, but balance. If you listen closely, you can almost hear it. The first breath of creation, expanding faster than thought, cooling, settling, preparing the stage for everything that would come after. Inflation was the universe's opening act, the great stretch that made room for all the stories to follow. And if this inflation never truly ended, if new universes continue to bloom beyond our sight, then perhaps the Big Bang was not the beginning, but one verse in a longer cosmic song, a song with no final note, always unfolding, always expanding, like the breath of infinity itself. As we drift further into that idea, we begin to see how this possibility opens the door to something grander still, a multiverse, a vast sea of realities, each born from its own great stretch. And in that sea may lie the answers to why our universe has the laws it does, and what might exist beyond the borders of everything we know. When the universe was young, so young that time itself had barely learned to tick, it underwent that brief, spectacular stretch we call inflation. But some physicists suspect that stretch never completely stopped. In certain corners of the cosmic fabric, it may still be happening right now, expanding faster than light, birthing new universes in its wake. This is the strange and beautiful idea of eternal inflation, a universe that keeps giving birth to universes forever. Imagine the inflationary field not as a single burst of energy that faded long ago, but as a vast shimmering ocean of potential. In some regions it settles, cooling just enough to form a stable universe like ours. In others, it keeps expanding, its energy never quite relaxing. Each moment, somewhere in this invisible ocean, a patch of space-time tips over into calm, forming a bubble. Inside that bubble, inflation stops, temperatures fall, matter coalesces, stars ignite. Outside, the inflationary field keeps roaring, stretching space at speeds no light could ever outrun. Every bubble becomes its own cosmos, growing quietly within an even greater sea that never rests. This is why scientists sometimes describe reality as a multiversal foam, a froth of universes forming, growing, and drifting apart. Each bubble is sealed off by the expansion itself. The space between them widens faster than any signal can cross, so no message, no light, no traveller could ever bridge the gap. The borders of each universe recede faster than the speed of light, like the surface of an expanding dream. Even if other universes exist right beside ours, we would never see them. They vanish from reach before the thought of reaching them can even form. It's a haunting image. An infinite ocean where new bubbles of reality constantly blossom, each glowing with its own physics, its own constants, its own possibilities. Some might be barren and short-lived. Others might teem with stars, galaxies, and perhaps even forms of life that will never know how close they were to countless other worlds. In this view, our entire cosmos, everything we can see, every atom, every galaxy, every whisper of light, is just one bubble in an endless sea of bubbles, one gleaming drop in the foam of creation. The laws inside each bubble depend on the conditions when inflation ended there. In ours, that transition produced the familiar fabric of space, the stable particles of matter, and the delicate balance of forces that make life possible. In another bubble, the numbers could be different. Gravity stronger, light slower, atoms unstable. Entire realities could blink out in an instant, or expand too fast for matter to ever condense. The multiverse, if it exists, would be a cosmic garden of possibility, blooming endlessly, with each flower following its own laws. Mathematically, eternal inflation arises naturally from the same equations that describe the original inflationary burst. When the inflation field loses energy, it doesn't do so evenly everywhere. Quantum fluctuations, the tiny random jitters of energy that pervade space, cause some regions to decay faster, forming universes like ours, while others remain inflated. Those surviving regions keep stretching exponentially, creating even more potential for new universes to form. The process feeds itself like an infinite chain of cosmic dominoes. There's never a final universe, never a last bubble, only the continual unfolding of new ones. To visualize it, think of rain falling into a still pond. Each droplet hits the surface and sends ripples outward, overlapping and expanding, but never truly merging into a single calm sheet again. Inflation is like that, except the pond itself is growing as it ripples. Each droplet is a universe, each wavefront a border that can never be crossed. The pond goes on forever, and the rain never ends. If this is true, then the universe, the one we speak of in singular terms, is not the whole story. It's a local chapter in an eternal saga, and the space between those universes, the vast inflationary sea, is not nothing. It's a fertile void, humming with energy, giving birth to new realities at every heartbeat of eternity. The physics that govern that higher sea are unknown to us. We are like bubbles looking inward, seeing only our own reflection, unaware of the foam that surrounds us. And yet, this idea also carries a quiet grace. It suggests that creation never really stops. Even as our galaxies drift apart and fade, even as stars burn out and space grows cold, new universes are still being born somewhere beyond the reach of light. The cosmos never dies, it simply transforms, continually recycling existence into new forms. What we call the universe may be only one note in an endless cosmic melody, always echoing, never repeating. There's something profoundly comforting in that thought. It means that even if our world ends, whether in heat, death, collapse, or silence, the story of being continues. Somewhere, in a new bubble, another dawn begins, another sky unfolds, another consciousness perhaps looks upward and wonders if it is alone. The multiverse doesn't erase our significance, it expands it. It means that existence itself is the constant, and every world, ours included, is a verse in the infinite poem of reality. Of course, eternal inflation remains a theory, not a proven truth. It's a bridge between what we can test and what we can imagine. There's no way, at least for now, to observe another bubble. Their boundaries lie beyond all communication. The evidence of their birth is hidden in the inflation that still expands between them. And yet, the mathematics fit so naturally, and the vision they inspire feels so harmonious with the patterns we already see, that the idea has become one of the most beautiful in modern cosmology. not as a final answer, but as a reminder that the universe may be deeper and more generous than we ever dreamed. If you close your eyes and picture it, a foam of universes, each glowing softly in the infinite dark, each drifting away faster than thought, you might sense the quiet wonder of it. Somewhere, another universe might be forming at this very moment, its own stars yet unborn, its own time just beginning to breathe, and between those bubbles the eternal sea keeps stretching, forever expanding, forever creating, like the calm pulse of infinity itself. As we drift further into this idea, the vision deepens. If universes can form and float within a higher reality, what then contains that reality? Could there be a deeper structure, another dimension beyond all this bubbling space? Our next step will take us into that possibility, to the idea that our entire universe might be just a thin film, a shimmering surface drifting in a higher dimensional ocean. If eternal inflation imagines universes blooming within an infinite sea, then brain cosmology takes that sea and gives it depth. It asks, what if our entire universe is just a thin film, a floating sheet, drifting in a vast higher dimensional space? The word brain comes from membrane, and in the mathematics of string theory, it's not just a metaphor, it's a way to describe reality itself. To begin, imagine that everything you know, every star, every atom, every thought, exists on a two-dimensional surface, like paint on a canvas. The canvas itself is invisible, but it supports everything painted upon it. In this picture, our universe would be that painted layer, a three-dimensional brain stretched across an unseen multi-dimensional backdrop known as the bulk. This bulk is not empty, it's a kind of geometric ocean where dimensions curl and fold in directions we can't sense. In everyday life, we perceive only 3 dimensions of space, length, width, and height, and one of time. But the mathematics of string theory whispers that there might be more. Not just 1 or 2, but perhaps 10 or 11 dimensions in total. Most of them are curled up so tightly that we can't detect them, like tiny loops hidden in every point of space, smaller than atoms, smaller than light itself. If you could zoom in far enough, you might find that every point of our universe isn't a point at all, but a doorway into countless curled corridors. Our universe, according to this idea, floats within that higher dimensional bulk like a film of soap within a larger bubble. Other brains could exist nearby, parallel universes, not above or below us, but alongside us in dimensions we cannot see. They might be separated by distances as small as a millimeter or as large as eternity, depending on how the bulk is shaped. If those other brains exist, they might carry their own versions of physics and their own matter, light and time, all invisible to us because our eyes, our instruments, even our particles, are confined to our own brain. We cannot see across the divide because light itself is trapped here, unable to wander beyond the sheet that holds us. Yet there might be one thing that does travel between brains: gravity. Unlike light or matter, gravity arises from the curvature of space itself, and if space extends into higher dimensions, then gravity could leak through the bulk. Some physicists have proposed that the apparent weakness of gravity in our universe, how feeble it is compared to other forces, might be because much of its strength diffuses into these hidden dimensions. We feel only the faint echo that remains on our own brain. To visualize this, imagine fish swimming in a shallow pond. They can see each other, hear the ripples they make, and feel the currents in the water. But the air above their pond is invisible to them. They can sense its effects, the faint dimming of sunlight, the coolness that follows rain, but they cannot swim into it. Now imagine another pond floating just beyond their reach, separated by a thin barrier of unseen water. The fish in one pond would never know the fish in the other exist, even though they are only a breath apart. To the fish, their pond is the entire universe. To us, looking down from above, the ponds are just two surfaces in a single greater world. Brain cosmology paints our universe in a similar way. We are the fish, and our space-time is the pond. The bulk, the higher dimensional reality, is the air around it. We can't step into it, but it might be closer than we think. Some models even suggest that the birth of our universe could have been the result of two brains colliding within that higher dimensional space. When they touched, the energy of their collision could have ignited a new Big Bang, a burst of heat and expansion that became our cosmos. In that case, the beginning of time was not an explosion from nothing, but a meeting, a cosmic embrace between neighbouring worlds. If that sounds romantic, it's because the universe sometimes tells its stories that way. Science often begins with questions of force and motion, but when it reaches the edges of what can be known, it turns almost lyrical. The idea of colliding brains gives the Big Bang a partner, a rhythm of approach and retreat that could repeat across eons. Perhaps our universe has siblings, each born from a similar collision, each drifting away into its own quiet history. The mathematics behind these theories is intricate, full of symmetries and folded dimensions, but their meaning can be felt more simply. They say that existence might be layered, not a single expanse, but many overlapping sheets of possibility. We live on one of those layers, sensing only what happens within it, unaware of the unseen architecture that holds us in place. It's a humbling vision, one that places us not at the centre, but as part of a vast cosmic fabric, fluttering gently in an invisible wind. And yet, despite the elegance of the idea, we have no direct evidence that these other brains exist. They remain a mathematical possibility, a whisper of higher order. Still, the fact that such theories fit naturally with the physics we do understand makes them hard to dismiss entirely. They offer a bridge between the quantum world, where everything vibrates like strings, and the cosmic world, where space itself stretches and bends. In some versions of string theory, our universe is not just a sheet, but a vibrating one. Each particle, each quantum of energy, is a tiny string oscillating in higher dimensional space, its vibration giving rise to mass, charge, and all the properties of matter. The fabric of space-time becomes a kind of music, a symphony of geometry. In that sense, brain cosmology doesn't just describe the universe's structure, it describes its song. Every dimension is a harmony, every vibration a note. If all this feels almost dreamlike, that's because we've stepped into a realm where the imagination and mathematics overlap. There is no experiment, no telescope, no detector yet capable of peering into the bulk. But perhaps we don't need to see it to sense it. The very fact that gravity behaves as it does, that the cosmos expands as smoothly as it does, might already be hints of that hidden architecture, the unseen ocean that cradles our brain. And maybe that's the gentle truth behind all these theories. The universe doesn't expand into something else, it expands as something else. Space doesn't need an outside to grow, it carries its own potential within. Each new dimension, each unseen layer, is not beyond the universe, but part of its unfolding self. As we drift onward, we'll explore how these hidden structures, the strings, the vibrations, the unseen harmonies, might tie all of nature's forces together. For beyond the mathematics, there lingers a question older than science itself. What if everything, from galaxies to quarks, is not separate but part of one grand equation still singing its endless song? If the universe truly rests upon strings and brains, then perhaps everything that exists is made of rhythm. Every atom, every particle, every flicker of light could be the echo of something vibrating in the hidden depth of reality. In the mathematics of string theory, the fundamental building blocks of the cosmos are not solid dots or indivisible grains, but tiny loops of energy. Filaments so small that if an atom were the size of the solar system, a string would be smaller than a tree leaf in orbit around the sun. And yet these invisible threads, vibrating in countless modes, may be the foundation of all that is. Each vibration corresponds to a different note, and each note becomes a different particle. A photon, the carrier of light, would be one particular rhythm, an electron another. Matter, energy, gravity, all might arise from the same instrument, played across multiple dimensions. The cosmos, then, is not a machine assembled from separate parts, but a single musical score, endlessly unfolding. Physicists sometimes call this dream the search for unification, the hope that all forces in nature might be woven together by one elegant equation. Long ago, the universe's forces were indeed united. In its first moments, there was no distinction between gravity, electromagnetism, or the nuclear forces that bind atoms together. As the universe expanded and cooled, these forces separated like harmonies splitting from a single chord. What scientists seek now is not just to describe that original chord, but to understand the instrument itself. Einstein spent the last decades of his life chasing this vision, the idea that gravity and electromagnetism, perhaps all of physics, were facets of a deeper unity. He never found it, but his pursuit planted the seed that became modern string theory. Today, physicists continue to refine that search, translating the elegant shapes of geometry into the trembling notes of quantum fields. Their work suggests that reality might be fundamentally musical, a structure that hums rather than merely exists. If we listen closely, that metaphor becomes more than poetry. Think of a violin string. Pluck it gently and it sings. Its pitch depends on its tension, its length, its thickness, the physical conditions that shape its sound. Now imagine a cosmic string, not made of wood or metal, but of energy vibrating in multiple dimensions. Its pitch would depend on how those dimensions are shaped, how tightly they are curled, how energy flows through them. Change the geometry and the note changes, a different vibration, a different particle, a new melody of reality. In this way, the universe might be not a random collection of forces, but a symphony played on the invisible instrument of space-time. The equations that describe it are like sheet music written in the language of mathematics. We don't yet know how to read all of it, but we can feel its rhythm. Gravity is the baseline, slow and deep. Electromagnetism is the shimmer of light, the melody that gives the world colour and shape. The nuclear forces provide the harmony that holds matter together, balancing attraction and repulsion in delicate intervals. Every star, every cell, every atom participates in that cosmic music, even if we hear only faint echoes of the full score. And though these theories stretch beyond what we can test, there's something quietly human in them. The search for a grand unified theory, or even the fabled theory of everything, is not just about equations, it's about belonging. It's about the intuition that the universe must make sense, that all its patterns and paradoxes are part of one continuous truth. Even if we never write the final equation, the pursuit itself reveals the harmony already present in everything we know. In a sense, the dream of unification mirrors the expansion of the universe itself. The further we reach, the more connections we discover. Each discovery doesn't fragment the cosmos, it reveals deeper coherence. Newton found unity between falling apples and orbiting moons. Maxwell united electricity with magnetism. Einstein bound space with time. And now, the physicists who chase the vibrations of strings are following that same path of synthesis, searching for the note that binds all melodies together. But the universe, like music, is more than its notes. It's also silence, the spaces between sounds, the pauses that give rhythm meaning. The equations may one day describe every interaction, every vibration, but they may never capture the reason those vibrations exist. Science may map the harmonies of the universe, but meaning still lives in the quiet between them, in the mystery that something is rather than nothing at all. Perhaps that's why even the most brilliant physicists speak of beauty when they talk about their work. when they find an equation that fits perfectly. It's not just correct, it's beautiful. Its symmetry feels inevitable, its form graceful, its logic serene. Beauty in this sense is a hint of truth, the resonance between human intuition and the deep structure of reality. The universe doesn't need to be beautiful for us to exist, but somehow it is. The mathematics that govern the stars also weave through our neurons, our art, our laughter. The same patterns that ripple across space ripple through our thoughts. Maybe that's what unification really means. Not just that all physical forces are one, but that consciousness itself is part of the same fabric. The equations describe motion and matter, but the music they create gives rise to awareness. You, listening now, are part of the universe's self-reflection, a small pattern in the grand vibration, aware of its own song. In that way, the living equation is not just written in symbols on chalkboards or coded into the laws of physics. It's written in light and sound, in the movement of galaxies, in the warmth of your pulse. It's a reminder that the universe isn't just expanding outward, it's also unfolding inward, finding expression in thought, emotion, and curiosity. Every time we ask why, we continue the same expansion that began at the dawn of time. Mathematicians may one day express this unity as a single elegant line, a formula that softly translated would mean all is vibration, all is connection. But even if that day never comes, the truth remains present in every heartbeat, in every photon that reaches your eyes. The cosmos is alive with equations it doesn't need to solve. It simply exists, and that existence is already enough. If you close your eyes and imagine that cosmic music, galaxies turning like slow records, atoms humming in their tiny orbits, gravity bending space like a drum skin, you might sense that the universe isn't a place we live in, but a song we are part of. Its rhythm pulses through everything, from the swirl of galaxies to the stillness between breaths. And so, as our story nears its quiet close, we return to the idea that began it all. Expansion. Not just of space, but of understanding, of wonder, of awareness. The universe continues to stretch, and so do we, reaching outward and inward, searching for harmony, finding it in the spaces between. Our final step will bring us full circle to the breath of the universe itself, and to the realization that all expansion, all music, all motion is part of the same unending exhale. And so, we return to where we began, to the quiet, expanding fabric that carries everything we know. Across all our wanderings through redshift and geometry, dark energy and hidden dimensions, the same rhythm has echoed underneath it all. The universe breathes. It expands and evolves not into something beyond itself, but as an expression of its own being. Space is not a container that stretches, it is the stretching. Time is not a current flowing through events, it is the unfolding of those events themselves. When we speak of the universe expanding, what we really mean is that existence itself continues to exhale. You can feel that rhythm even now in your own breathing. The slow rise and fall of your chest mirrors the cosmic pulse. The same balance between expansion and stillness. Every galaxy's drift, every photon's redshift, every stretch of space-time is part of that vast inhale and exhale. The scales are unimaginably different, yet the pattern is the same. The microcosm and the macrocosm share the same heartbeat. When scientists describe the universe's expansion, they do so with extraordinary precision, measuring the way distant galaxies recede, calculating how quickly that motion accelerates, mapping the geometry that determines its fate. But behind those measurements is something simpler, almost tender, the recognition that everything changes. Expansion is a scientific fact, yes, but it's also a philosophy of impermanence. Nothing stays still. Stars burn and fade, light stretches, Atoms combine and part. Even silence is movement waiting to be heard. Perhaps that's why the language of cosmology so often turns to poetry. When we describe the birth of space, the dance of galaxies, the flow of time, we find ourselves speaking in metaphors that sound like breath, like music, like water. Science, at its edge, always touches the ineffable, the point where numbers turn into awe. The universe expands, but into itself. It has no edge to cross, no external emptiness to fill. Each new region of space is not added, but revealed, like a flower unfolding its own petals. The surface grows, yet the centre remains everywhere. You, where you're sitting now, are just as central to the universe as any galaxy, any cluster, any distant quasar. There is no privileged viewpoint, no cosmic capital. Every place is the middle. Every observer sees the universe expanding away from them in all directions. Not because we are special, but because the universe has no single anchor. Every point is the centre of its own horizon, and all horizons are true. That, perhaps, is one of the quietest lessons of modern cosmology. There is no up or down, no edge or middle, no before or beyond, only the smooth, ongoing bloom of existence. The universe doesn't expand outward, it expands within. It is self-contained, self-creating, self-sustaining. Its motion is its meaning. Think back to the first moments of time, to that blazing density where space and energy were indistinguishable. What we call nothing then was not emptiness, but potential. The universe emerged not from an explosion, but from a transition, from stillness into expansion, from possibility into form. Every galaxy, every molecule, every thought since then is a continuation of that same gesture. Expansion is not a past event. It is happening now, and always. You can see it in the sky tonight. When you look at the faint light of a distant galaxy, you are witnessing the memory of that expansion. The light has travelled for billions of years, stretched by the growth of space until it arrives as a whisper of colour. It carries not just information about distance, but about time, the way the universe has aged and evolved. Every photon is a message from the past, softened by the journey, slowed by the expansion that keeps going even as you read this sentence. And that expansion, though vast, is gentle. The universe is not rushing anywhere. It simply flows. Its acceleration is not a frantic sprint, but a serene widening. It is not explosion, but breath. Perhaps that is why so many scientists, when they finally confront the scale of it all, find themselves speaking of wonder rather than conquest. To study the universe is not to master it, but to listen to it, to hear its slow pulse in the language of light. There is a quiet symmetry in the idea that the universe began from nothing, and still carries that nothing within it. Every atom is mostly empty space. Every galaxy is separated from its neighbour by gulfs so wide that even light takes millions of years to cross them. The universe is, in essence, a structure of emptiness, but an emptiness alive with pattern. The same silence that existed before time began still hums between the stars, stretched thin but never broken. Maybe expansion is the universe's way of remembering that silence, keeping a trace of its origin even as it grows more complex. When we step back from equations and telescopes, what remains is a feeling. Gratitude that there is something instead of nothing, and that this something is so exquisitely balanced between simplicity and depth. The universe did not need to produce consciousness, yet it did. It did not need to become beautiful, yet it is. Out of the quiet breath of expansion arose light, matter, life, thought, and eventually wonder itself. So, when we speak of the fate of the universe, whether it will freeze, rip, or drift into endless calm, we're really speaking about the continuation of that breath. Galaxies will drift apart, stars will fade, time will stretch thinner and thinner, until the sky grows dark. But that darkness will not be an end, only another kind of beginning. Even in silence, the breath continues, expanding beyond our comprehension. The universe will keep unfolding, patient and eternal, while we, its small and temporary listeners, fall gently back into its rhythm. Perhaps expansion is not a sign of distance, but of memory. Perhaps the universe expands because it cannot stop remembering the moment it became. Every ripple of light, every echo of gravity, every atom spinning quietly in the dark is part of that remembrance. Creation, it seems, was not a one-time act, but an ongoing conversation between being and emptiness. And we are the witnesses, small, luminous thoughts rising from the same silence that once sparked the stars. So as you sit here, maybe late at night, maybe under dim light or fading stars, take a slow breath. Feel it move in, feel it drift out. That is the rhythm of the universe itself. The galaxies breathe too in the language of expansion. Time breathes, light breathes. Everything that is alive does, in its own way. You are part of that same motion, the same exhale that began billions of years ago. And in that realization, perhaps the universe stops feeling distant. It becomes what it always was, close, continuous, familiar. Not a mystery to solve, but a song to listen to. A song that began in silence and will one day return there, softly, carrying us with it. And so, we end our journey here, at the quiet edge of knowing. The universe expands, and so do we. There is no rush, only the long, patient breath of existence, still unfolding, still beautiful, still awake,